right, we are live on YouTube and we are live on Zoom. All right, awesome. Hey, welcome. I see we got a couple additional folks. Hey, Lars. Hey, Remo. How you guys doing? Good to see you guys. So again, my name is Sonny White. I'm the Director of Advanced Research Development here at. Stand by. I'm getting. Apologies, that was a problem with the organic interface here. My YouTube thing was playing at the exact same time. Anyway, sorry. My name is Sonny White. I'm the Director of Advanced Research Development here at Limitless Space Institute. This is the LSI Grants and Fellowships midterm briefing. And so we're getting a chance to share everybody's work with the public. So looking forward to hearing from all of our principal investigators. Before we get started, I would like to share just a little bit about Limitless Space Institute. And then we've got our keynote here, Andrew Duggleby from Venus Aerospace. They're doing some awesome things with trying to figure out how to make rockets go incredibly fast, right? So we're looking forward to hearing from you today. I won't take too long with my part because I really want to get to the point where we can hear from the folks doing all this amazing work. So let me share my screen here. And I think, Andrew, for when I switch to yours, you have video with sound, correct?
Yeah, yes, I'll share sound.
Okay, so let me share sound. I think I'm going to share sound. Try one more time.
Maybe PowerPoint too. Select your PowerPoint too.
That's, yeah. Well, I'll give you a rocket noise when we show your video, right? So we're having some issues with sharing sound. The option is grayed out. So, but we'll go ahead and press ahead, right? So, can everybody see my screen? Okay, awesome.
Yeah.
Okay, so Limitless Space Institute. So we are a 501c3 nonprofit. Some of you already know that are watching online. We have a very unique mission that we're trying to pursue. Our mission is to inspire and educate the next generation to travel beyond our solar system and to support the research and development of enabling technologies. The three pillars of our implementation of this consist of inspire, educate, research, right? We want to inspire folks to want to go try and figure out and educate themselves on how to do some of the amazing things that they see and hear about so that they too can one day go do the research that's necessary to make some progress. And then that will in turn serve again to inspire some additional folks later in time. And so the process kind of continues. It's this inspiration circle of life, not the circle of life where things eat each other. That's a different one. This is more trying to map to making the world a better place. Our pinnacle objective is to work to enable interstellar travel by the turn of the century, and that is exceedingly difficult. But LSI is a doing organization. We do try our best to put rubber on the road. We conduct research internally. We conduct research in our lab, EagleWorks, that's here just about 50 feet from where I'm sitting. We're currently working on some nanotechnology, working in partnership with Texas A&M and Isentis to explore some foundations of physics ideas to see if we can figure out, are there some new ways we can do things to generate power? Are there some new ways to do communications and sensors? And so there's a couple of pictures there, scanning electron microscope picture of some very tiny things that we've been working really hard to learn how to make effectively and experiment with in the lab. In addition to that, we have our LSI Grants and Fellowships program. This is the reason we are here today. And so this gives us a chance to directly support universities, professors, and students all over the globe that have very similar interests to us and want to try and spend some time and effort and do that very early foundational work to try and develop capabilities that allow us to figure out how do we get past Mars with human beings in the solar system? What would it actually take to get to another star system? And so some of the types of topics that we have funded in the past and are part of this class that everyone will hear from today: beamed energy propulsion, solar sails, fusion propulsion, getting into the frontiers of physics in the form of space drives. How do you push off of the fabric of space-time or the quantum vacuum? Is that even possible? And space warps and wormholes. They're mathematically possible. We have no idea how to build those. And so we're funding universities to do work to try and make progress on those types of ideas. And so we do that in partnership with Texas A&M and one of our cousin organizations, Breakthrough Initiatives. In addition to that, we also have our Limitless Educator program. So this is a program where we partner with teachers in the K through 12 regime to develop classroom materials to try and teach and get kids excited about space exploration, to maybe want to get into the STEM fields that are directly connected to all the different types of technologies that are parts of these systems of systems that we use to go try and accomplish these missions. We also have university partnerships. This is where we get opportunities to directly partner with other universities that are interested in work that we're doing as well. And we do this, it's almost like a partnership, if you will. No resources pass back and forth other than we're both leaning in and pushing on the same rock. And so we've got a partnership with Texas A&M, and we actually just signed some paperwork with Baylor University very recently. Now, just to kind of highlight and set a bit before we start hearing from our guests and our principal investigators, when we talk about getting human beings past Mars in the solar system, I mean, what does that even mean? How would that even work? It's exceedingly difficult. And to kind of illustrate that, consider the following. If we wanted to get a human crew to Saturn, and we want to get them there in 200 days, the amount of energy that's necessary to make something like that possible is an order of magnitude more energy than it takes to get a payload from the surface of the Earth to low Earth orbit. So all that to say, chemical propulsion cannot close that kind of an architecture. We have to have other things to be able to do that kind of mission in that time frame. And so you'll hear from our investigators some of the ideas that they have to try and accomplish these types of objectives. And we have a lot of partnerships that we've already formed with a number of universities all over the globe. There are additional ones in work even now. And so we hope to continue the tradition of LSI Grants and Fellowships in a biennial process where we do this every 2 years, and we continue to provide support to universities all around the globe that are trying to do some work in this domain. So this is a schedule of what we're going to go through today. First up, we'll hear from Andrew from Venus. Thank you, Andrew, for being here with us today. I've known Andrew for a while. He's a fellow spacewalk, very excited about trying to figure out how to make things even more effective for space flight. So looking forward to hearing from him. We'll hear from 4 of our investigators before lunchtime, Houston time. We'll have a little bit of a period for Q&A at the end of that. So we're kind of keeping this streamlined and tight. So we'll have a 20-minute facilitated Q&A around 11:50 Central Daylight Time. And so we'll be taking questions from folks on the Zoom webinar. We'll be looking in the chat for that, and we'll try and bounce back and forth on the YouTube channel to look for that. We'll take a 20-minute break, and then we'll go into the afternoon session with the remaining 5 performers talking about what they're doing, again with another 20-minute Q&A at the end of that. So trying to keep all this stuff tight, and this is all recorded to YouTube, so it'll be available afterwards as well. So I think with that, let me hand the microphone over to Andrew. Andrew is the COO of Venus Aerospace. He's got a long history of working in the space program. So Andrew, let me just kind of hand the microphone over to you. I'll bring up your charts here, and I will, when the time comes, I'll make sure I give you a rocket noise. So
Great.
Sorry to interrupt. Hi, Kieran here from Breakthrough Initiatives. Sunny, am I right in thinking that this recording is going to be on YouTube?
It's actually streaming on YouTube right now.
Okay, great. All right.
Awesome.
And it will be available after?
Absolutely. It'll be available after. So, and I'm really glad you got a chance to join us today. I think you're in a very different time zone as well, right? So.
Yeah, in Luxembourg.
Very good. Very good. Thank you for joining us. So.
All right.
Andrew.
Appreciate the intro. Thanks for having me here. As I mentioned, co-founder and CTO of Venus Aerospace, and I appreciate the invite here as I might be the person working on the slowest form of propulsion. So
I haven't met a rocket I don't like.
Yeah, only trying to go hypersonic, not quite trying to go to Saturn. And really what we're doing at Venus Aerospace is we are trying to extract that last little bit out of chemical energy. So I'm going to talk to you a lot today about our rotating detonation engine, right? And detonation just being the scientific term for supersonic combustion. So we sort of have one last trick up our sleeves in the chemical world before we're topped out.
Mm-hmm.
Right. But just a little bit of background about myself. I had actually, after getting my PhD, started off in academia. I was a professor at Virginia Tech and then ultimately at Texas A&M University. And really, this is I always joke I was a third generation professor. So this is, my mom was a dean and my grandfather was a dean. And so I had
it was inevitable, right?
It was inevitable, right? I grew up where, how do you go change the world? Well, you go to get a PhD, you go to university, and then you work on changing the world. You were promoted to. Yeah, and I'm in the Navy Reserve.
Yeah.
So just got promoted last year to lieutenant commander.
Yeah.
And while I was a faculty at A&M, though, I started as a business with one of my students, and so then I also discovered the power of entrepreneurship. And so when I exited that first business, I decided I exit academia altogether and go work for Richard Branson. So we were out in Southern California, putting a rocket on the wing of a 747, and we're ultimately successful there. But it was really, it's been really fascinating to sort of straddle both worlds of academia and what's possible with new space. And so all of this really leads up to, this vision of, well, how do you go and move things faster? How do we go fly hypersonic speeds and cross, say, the Pacific Ocean in 1 hour? How do we do San Francisco to Tokyo in 1 hour? How do we do London to Houston in 1 hour? And I have to admit, I was very much a rocket person. And so I was always thinking about the detonation engine we're going to talk about today. I was always framing it from a rocket point of view, that this was an engine that would then, quadruple our payload going into space. So this is how we would then finally go mine asteroids or do a moon colony. But as I mentioned, I'm in the Navy Reserve, and in 2018, the U.S. Navy had a couple collisions at sea. So the shipyard in Tokyo Bay was overwhelmed, and I was asked to activate and go help. And so, spending time living in Japan, that finally made that connection for me, which is, not only would this detonation engine make a great rocket, it is finally efficient enough that you can put it on an aircraft, albeit an advanced aircraft, and push across the globe in an hour. And so that was kind of the basis of the idea. I was sitting there in Japan, and then my colleague at Purdue University in roughly 2019 timeframe, Steve Feaster, he published a paper and sort of finally showed that this detonation engine thing was worth the squeeze. So he showed about a 10% gain in ISP over standard rocket engines. And so that was sort of the moment for us of, hey, this technology is now here. I knew from being a faculty that, just how far you can push a technology in academia before you need an order of magnitude more dollars. So we knew we had to go found it. But really the technical side of the story, I'm actually going to start in the past, which is hypersonics is not new. It's actually very old. So most people will remember the X1, which was Chuck Yeager breaking the sound barrier. Not many people remember the X2, where we crossed Mach 2. And not too many people remember the X15, where we went Mach 6 on a regular basis. So the X15 did 199 flights in the 1960s. And it was a rocket plane. So this was carried under the wing of a B-52, but then they dropped this rocket-powered airplane. There was a human in the loop in there, and they pushed to Mach 6 and 100,000 feet. Now this vehicle had multiple missions. It also did some exoatmospheric and reentry studies, but really this was Mach 6 in the 60s. And to frame the value of the engine I'm going to talk to you about today, if it was the right, if we got it big enough and put it on the back of this X15, it would not go Mach 6, it would go Mach 9. So really that's what framed it. So detonation engines, we'll kind of dive in. And in the end, like I mentioned, detonation is just supersonic combustion. And the video I'm going to show you is from our hot fire here in Houston. We've set up over the last year an engine test stand. And so for any of you who are down here in the Houston area, it's sort of an open invitation to hit me up and we'll kind of get you over there and show you some testing. I don't think the sound is working, but if you go, we have this, the video I'm showing you is released elsewhere on YouTube and places, so you can go take a look at our video with sound. And what you're going to notice is, so Sonny will make a rocket noise and then I'm going to whistle. Because what happens with the detonation engine is that once you transition over to detonation, you end up standing a detonation wave that's going round and around this annulus about 20,000 times per second. And we actually end up hearing some of those pressure waves as whistles. So quick video.
Yeah.
Yep, go. Sound.
Well, we can hear if they can't.
There's a whistle. So what you just watched was, this is jet fuel hydrogen peroxide, but this is the view end on into that engine. So high-speed camera, and those waves are going back and forth about 20,000 times per second. So as you keep putting more fuel oxidizer in the system, the detonation waves just keep going hungry to go. All right. So since this is a technical crowd, I wanted to have a few more technical slides. So there's been some really good CFD work out there trying to examine detonation. So I grabbed one from 2019 from Converge here, but this is the blue would represent your fuel and oxidizer that has been mixed. But the idea here is don't start to burn, otherwise you're doing things of deflagration. And then the detonation wave that's coming around the corner, right, about 20,000 times per second. That has a shock wave that ultimately raises the pressure and temperature, and then you get into detonation. So kind of as a little PowerPoint engineering here for you, but as you watch this detonation wave now come in, if you look at the right, this is sort of the very simple example of what's been going on. You have injectors that are pushing ox and fuel in. You've got the two of them mixing but not combusting. And then when that supersonic front hits, the shock wave actually creates a very small zone where the temperature and pressure have been raised. That's enough for our purposes for hydrogen peroxide to then split into steam and oxygen, and then it ultimately is the oxygen and the jet fuel that then combusts in our application. So you get that combustion, and then the exhaust, and then your injectors recover and kind of push more for the next wave coming around. Thermodynamically, this looks like this. So I took this from Jay Gray's Engineering Physics 2018, but this effectively lets you achieve constant volume combustion as opposed to constant pressure combustion. And if you kind of do the area under the curve from a work point of view, the theory says we should see anywhere from say 10 to 20% extra ISP coming out of this, right? Because you get constant volume combustion, you end up having higher pressure and temperature. And I have one request for everybody on the YouTube channel and Zoom is next time you see a rocket launch and you see the big bright tail and it looks really awesome and inspiring, I actually want you to shed a tear with me. Yeah. Because what you're actually observing is all the thermal energy that we were unable to extract from that combustion.
Let's have a moment of silence.
So a little moment of silence for really hot and bright thermal plumes. Yeah. So with this combustion, it is also called pressure gain combustion because you get more combustion. You also get a little bit higher temperature. You're ultimately able to extract more of that thermal energy and turn more of it into kinetic energy by about 10%. And really to frame 10%, that's a big number. The SpaceX engine on their Falcon 9, right, their Merlin engine is roughly only 2% better than the Apollo engines. And that 2% was well fought for through the decades by many smart people. So 10% is a very significant challenge. Very significant.
Definitely worth chasing down if you can do it, right?
Yeah, absolutely. And then, because we have an annular combustor, the other thing that we get to do, and this has been, people have talked about doing an Aerospace engine in the past. You go through the math, you see the performance advantages, you go do your system engineering, it's very possible all the extra mass behind the Aerospace nozzle eats up all the gained performance. But really, as you increase in altitude, going from kind of sea level up to vacuum, as your outside pressure adjusts, what an Aerospace nozzle does is effectively make sure you have sort of this pressure matching. So you also are maximizing or minimizing any pressure losses from the engine. So both are working here for us to go do that. So, what have we been doing so far? Well, the first thing that Venus did over the last year is we have gone to jet fuel and hydrogen peroxide. This is important because ultimately we are chasing aviation. All right, my past job, I was head of launch operations for Virgin Orbit, and we dealt with cryogenic liquids, right? Cryogenic liquid oxygen. It takes very long to step into a rocket launch, as days, right? Usually 2 days. And then if you have a valve freeze or if you have your system warmed up because you took too long doing something, not only might you miss your actual launch window for the satellite, but you may actually have kind of timed out your thermal clock. You actually need to step away from operations. And it would take another 2 days to step back into rocket launch. So we, knowing we wanted to get after sort of Mach 5 to Mach 7 flight, and this more of an aviation problem, we spent the last year getting into room temperature storable liquids. So that's been some of the work we've been doing. So ultimately, we've got an engine that makes a lot more performance. I'll talk about our heat profile here in a second. Reusability, it was the big key here. Again, aviation, storable and stable. And then this might sound really weird to most people, but it turns out from an energy perspective, it actually makes more sense to keep accelerating than get to a top speed and just maintain. So really, just by kind of keeping accelerating, the overall carbon put into the atmosphere for a system like we're doing is actually less than current aviation. That's pretty interesting. So, what are we doing? Here's kind of the three things I was mentioning: X1, X2, X15. So we're actually coming back and slowing down. So first thing, we're just going to slow down. We're going to add jet engines and landing gear. The X15 had a nose landing gear, but then skids in the back. And we're going to kind of give it an upgrade. The first thing we're doing with this is actually flight testing. So there's lots of needs for real flight testing of whether it's materials or scramjet engines, you name it, at kind of Mach 5 to Mach 7 regime. So that, as a business point of view, is our first market. And then ultimately we want to come back, make larger vehicles. And then, our ultimate dream is the Stargazer. That's going to be a while. Very, very clear here. That's 20, 30 years later to get all the way back into sort of human rated aviation at those kind of speeds. And, what are we doing? Ultimately, the value in a low flying rocket, I hope everybody here has at least watched Top Gun Maverick. It's a very fundamental, for people who like to go fast. The opening scene was quite exciting. But as you saw depicted in the movie, the challenge of gathering your oxidizer from the air means you have to fly low. So that would represent the gray curve on the screen, right? How do you make jets go fast? So you lots of interesting challenges, but ultimately you have to keep flying low in order to feed your engine. The consequence of that is your vehicle temperature gets pretty high, and it might be 2,000 degrees, it might be 2,200 degrees, but those are some pretty big thermal problems. Of course, in reality, if you hit eject, I don't know that you survive at Mach 10. And certainly you probably need more than a glass of water, which is all Tom Cruise strength. But the idea behind low flying rockets, whether you're the X-15 from the 1960s or what we're looking at doing, is you carry your own oxygen, so you don't have to fly low. You're no longer constrained to fly low. Now your only constraint is stall, right? Just fly low enough that you still are maintaining a flight condition over your wings. And so that's kind of each of these three bullets you're seeing here, whether it's our sort of initial drone at Mach 5, or a potential Air Force drone at Mach 7, or ultimately this sort of passenger drone at Mach 9. All these represent about 800 Fahrenheit on the vehicle, so that's much easier to handle. And if there's any aviators in the room, this is about 400 knots equivalent airspeed. So if you were, the air pressure on your vehicle is about the same as 400 knots at sea level. So that's kind of represents what we're flying. So that's the Venus plan, and for us, because ultimately this is a business, that's a fascinating part of kind of straddling the R&D all the way into the business land. There's real markets here for us as business to go chase. So ultimately, first the flight test defense, then ultimately that dream is commercial aviation. And to us, that's what keeps us going in the middle of doing all these hard things that we're doing. It's the simple question of what changes if you can fly across the world in an hour. The idea of working in San Francisco, boarding a plane at noon, and then an hour later you're in Japan, and it's 7 a.m. You go to a factory or you go to a business meeting, and for 3 hours you're having a face-to-face meeting. The Japanese may be drinking coffee because it's their morning. You may be drinking an afternoon beverage because it's your afternoon, but it's jet lag free face-to-face communications. And then if you so wanted, you could board a plane and be home for dinner. So for us, that's really where we're going.
Yes, please.
Yeah, absolutely. And kind of both in that sort of now, near, and far markets for us as we're getting into each one of these operations. So, it's 2023. We have got our engine roaring. The next big kind of milestones for us, and I'll kind of leave it on this page. The next big milestones for us represents, the longer engine duration test. We've already done a couple. I'm not ready to share that with the world yet. But what you do in the rocket world is you sort of test against copper. Copper is cheap. You're going to blow up an engine, please blow up just a hunk of copper. You ultimately then 3D print the engines with cooling packages, right? That's what we have coming up in the fall. So you get more into like 30 seconds, couple of minute durations. And then you start putting on a vehicle. So we've already flown a subsonic drone. We have a supersonic drone that is going to be ready for flight this fall and start going faster and higher the whole way. And this is the picture of the team. Really, it's a phenomenal team. Most of these people have spent their careers doing crazy things. So this is everything from SpaceX to Northrop Grumman to Rocket Lab, GE, right? Just a phenomenal team of people from both the aviation side of aerospace as well as the rocket side of aerospace, and kind of bringing that world back together since the first time in the 1960s. So that's Venus Aerospace. That's what we're up to. And
Andrew, thank you for the briefing. This is good stuff. I really appreciate it. And we every single person on this call, like I said, probably hasn't met a rocket they didn't like, right? So
yeah,
it's neat to see and hear some of the thought process. I think we have just a few minutes for questions, because I know you may have to pop off and go to the office, go continue to do some awesome stuff. But maybe just to give some folks an opportunity to do some questions. Do we have any questions from the panelists?
Can I ask a question?
Yes, please. Absolutely.
Yeah, really inspiring stuff. And I wanted to ask about the control and piloting of these systems.
Yeah.
What's kind of the main thing you guys think about when you think about whether it's better or it's safer to have a drone fly it than a person? Like, is there a certain speed at which it starts to get just way safer to do it as a drone?
That's actually a fascinating yet old discussion. If you go back to the early days of rocket launch, right? The initial astronauts Gemini program, right? It's a big fight. Like, no, I'm here to fly the vehicle. And the rocket people are saying, no, that human error is not acceptable, right? So the first easy answer is that for your nominal flight, it's always going to be some sort of automated trajectory. So whether you're talking about the ultimate version that has passengers on board, it's going to be automated, or even if it's a drone, right? You would not do sort of a manual remote control of that drone just because the flight profile. A human may start flying towards Tokyo and then veer a bit too much left, and now you're landing in Kyoto, right? I hope everybody wanted to go there instead. So all the nominal for sure would be very tight controlled. Where the human really adds a lot of value, and I have some friends working some really cool automation and trying to get sort of the humans out of the loop, if you will, in aviation. But it's still all of the emergency procedures. If you have an engine out, what are you going to do? Right? You're boosting up and then you're crossing 100,000 feet, and then there's an issue. What do you do? Right? If you took off from San Francisco, can you now divert to Seattle? Have you gone too far? It's actually all of those things that we, super excited to the people who are working through the challenges of how do you remove at least maybe one pilot from the loop. But it's really the piece where humans still excel, honestly, is emergencies and quick decisions and all the pilot training. But to maybe the other half of your question, what's nice about flying at the altitudes we do, I kind of mentioned it's 400 knots. Really, the control surface or reaction speed, it would feel like you're flying a 400 knot vehicle, right? Which is okay. Yeah, it's not, doesn't put it into a regime where either the human can't react fast enough or say a computer can't react fast enough.
Okay. Yeah. Thanks.
Got a question from Lyndon Zinsky online. Will the flight be limited to over water?
Yeah.
Due to the sonic code?
Yeah, absolutely. Initially, right now, it is illegal to fly supersonic in the United States. However, Congress right now in their FAA legislation draft that we kind of help be a part of they are asking the FAA to sort of write down an altitude above which there's no speed limit. Why is that? Nobody in Kansas looked up and said, what the hell was that as the space shuttle went overhead? Nobody, right? So we sort of know from all the space shuttle data, Apollo reentry data, all of these things, that answer is somewhere in 110,000 feet, 100,000 feet, 110,000 feet, but where you can't even hear it. It's inaudible to the human ear.
Yeah.
So really, excited for the FAA and NASA to kind of dig in and kind of, write that one down into law.
Yeah.
But as it exists right now, for sure, you're not allowed to go supersonic over land. And so, all the initial markets would either be trans-Pacific or transatlantic.
Awesome.
Okay.
Well, thank you, Andrew. Really appreciate you giving us some of your time today. I'm going to switch gears now and get ready for our next one. We've got first up on part of our investigators, we've got Andreas High will be joining us from University of Luxembourg. Andreas is giving us a presentation on his work. The title is Extremely Lightweight Solar Sails for Fast Deep Space Missions. And so I tell you what, once you get started, Andreas, I'll give you like a 3-minute warning when we get to the end of the 20-minute slot. So if everybody else would make sure they're muted, and then Andreas, you have the con, sir.
All right, I hope you can hear me and see the screen.
Yes, we've got your screen and we can see your mouse.
All right, great. Yeah, so thank you very much for this opportunity to give an update on our project called Elvis. And there's absolutely no reference to any real people here, but I can only say that the project is alive and kicking. I'm here today with my colleague Lars Beeks, who has been focusing on the computational mechanics part, and he's also gonna explain his research in the context of this project. Just to start off, you've probably heard about interstellar objects, Oumuamua, and what's really fascinating about this technology of aerographite-based solar sails is that we can reach these objects which are between the stars, and we can do that within timeframes of maybe half a year or so. And we have just recently discovered these objects, such as interstellar objects, but also rogue planets, etc. And this is really a technology which could pave the way towards exploring all these objects which lie between the stars and ultimately even go to the stars. Now, what is aerographite? Aerographite is a material which has for the first time been publicized in 2012 by researchers in Germany, and it's a material which has a sponge-like consistency. It's mostly empty, and it has fairly peculiar mechanical properties. So you can see here these tetrapod structures which are interlinked in a stochastic way. These tetrapods are inside empty, and therefore the structure they're composed of is what they call a stochastic network. Yeah. And because of these properties, any sail which is created by aerographite has the potential to really exploit this potential or these mechanical properties. Now, why is aerographite so exciting as a material for solar cells? Because of its extremely low density of 0.18 kilograms per cubic meters, which is orders of magnitude lower than currently existing solar cell materials. Now, our project has 3 objectives. So we start with the existing literature. So there's literature on aerographite, and there's literature on using aerographites for sailcraft. Now, based on this literature, the gap we're trying to address is really getting from this initial concept of aerographite sailcraft to really something where the engineering works. And in order to do that, we first have to see whether we can actually create an aerographite sail, which is very thin, because the performance of the sail depends highly on the thickness of aerographite, and it's quite unclear whether that micrometer scale aerographite structure or sail can withstand all the loads during the mission. So this is a very important objective to address. Based on these results, we also want to find out whether there are feasible sail designs that can actually exploit these properties of aerographite, and also whether we can integrate different subsystems which are typically part of a spacecraft, such as power subsystem, communications, the payload. Can we integrate all of these elements into a coherent system architecture which is feasible? And hopefully addressing these objectives will get us from TRL1 to TRL3 at the end of the project. Now, in terms of the methodology, in order to address objective 1, we use multi-scale simulations, and Lars is going to talk about this in the following. We use finite element simulations for addressing the second objective, and for the third objective, we used techniques from systems architecting, such as trade space exploration and concurrent engineering. This is the team. We have a few senior researchers involved in the project. Lars and myself are present here, but we also have Camilo Suarez and Lavinish Rana, all from the University of Luxembourg, involved. And we also have a number of students who are currently working on the project and or have been working on the project, and I will explain that also in the following. So just to start with work package 1, which addresses objective 1, so really simulating these micrometer scale aerographite structures. We are currently at this second step, which means that we were trying to model the macro and microstructure of the sail, and ultimately run simulations in order to see whether that sail can withstand certain loads which occur during the mission. And we have currently Anshu Mehra and Jun Udis working on that particular project. And with that, I'm going to hand over to Lars. I hope it works.
That's me, yeah. Next slide, please. So I'm Lars Beeks. We can skip this, you just showed it. Let me introduce what we are trying to do in a bit more detail. So we think about a solar sail. Here you see a circular shape, but it could be any shape. And the idea is that this is at the scale of meters. We want to use a standard continuum finite elements for that. But to assess whether or not the sail would break, we want to take some critical points. Maybe you can go to the next slide. So we take some critical points where we see high deformations. And then we want to take those deformations and apply them in a smart way. Next slide, please. On the microstructure, on a microstructural model, where that would be on the scale of these tetrapods that Andreas showed. So, and the idea is that we don't apply that deformation to one microstructure, but to, let's say, a couple of hundred microstructures, because we don't actually know what the microstructure at that location is. So we want to do it in some kind of stochastic, probabilistic way. So that's roughly the idea of the little work package I'm involved in. The next slide, please. So we need a couple of ingredients. We need a macro scale model. So that will be on the engineering scale, in which we don't consider any microstructural features. And Erika Vita will finish that very soon. Then we have somebody who will create, that's Anshu, she will create the actual geometry based on Laguerre tessellations. She started not too long ago, and I won't discuss that. Somebody else will develop actually the finite element methodology for that, and we're going to use Timoshenko beams. They're quite well known, but we want to have an built-in code, so that we in-house built code, so that we can run thousands of or hundreds of simulations at the same time, because that's what we intend to do. And if you need an Abacus license, that's more expensive, let's say. And in the end, somebody will bring it all together in this computational, in this multi-skill framework, and that is Camilo Suarez. And I do nothing, I just talk about it. So maybe next slide. Yeah, so our microscale model, well, for now we've just taken a microscale model. For now we've just taken a circle. And the nice thing about taking a circle is that we have analytical expressions for that, but with finite elements you can do any type of thing. But here we can compare the analytical, the simulation result with the analytical result. So maybe next slide. Yeah, so we use plate finite element. Oh, sorry, yeah, shell finite elements are pretty much the same. We just consider linear isotropic elasticity, so no large deformations for now. We say initially we started with at the edge, so the circular periphery. There we keep everything fixed. Then we have a pressure due to the photons that hit the solar sail. We have the gravity of the sun, or whatever planet you want, but we take the sun. Heating we didn't do yet. Next slide, please. So now, okay, previous slide, please. Yes, thank you. So what we're going to do now is we're going to apply this pressure due to the sun, due to the photons, and we're going to and our solar sail will deform, and it will pretty much, let's say, blow up a bit. So what I'm going to do is I'm taking a point at one location around the solar sail, and then move through the center to the other side. And then we investigate what is the profile, the out of plane displacement. So next slide, please. And here you see that the analytical result and the, let's say, simulation result are exactly the same. Next slide, please. But the one too fast. Yes. But the problem is that we have quite a bit of deformation. So our solar sail is 20 meters as a radius of 20 meters. And our out of plane deformation is 13 kilometers. So that means that we don't have small deformations. We have very big deformations. So what went wrong here? So next slide, please. So what we did in a static simulation is we have the sun shining happily on our solar sail, but we apply at the edge of our solar sail, it's in black, we apply completely static boundary conditions. So we prescribe that the displacement of the periphery of the solar sail cannot move. This is pretty much the same as holding something rigidly on the ground, and that's of course not the case, because in reality this thing will start to accelerate. So now we go to the next slide. So what we did next is we did an inertia relief simulation. I never heard about it because I never worked in space before, or space applications. But what you effectively do is you say, well, there's a mass attached to my structure, and the structure itself may also have a mass. Before you do the actual simulation, you say, how fast will this thing accelerate if we end up with some steady state behavior, where the acceleration, it just keeps accelerating, but all the local vibrations have damped out. And then after you have computed that, then you do, roughly speaking, a static simulation. And what we have shown so far, next slide, please. Oh, so yeah, okay. So when you you can look at it as follows. If this mass that hangs on the solar sail approaches infinity, so if it's infinitely fast, you don't accelerate at all, and the displacement of the solar sail would be exactly the same as in the static simulation. So that's what I'm going to try to show now. Next slide, please. So here you see how much the solar sail deforms. So what is the maximum out of plane deformation? So in red, you see the result of the static simulation. And in blue, you see that if you increase the mass, it will eventually approach the result of the static simulation. Next slide, please. And if you then plot it on a log-log scale and you look at the difference, you see that this, on a log-log scale, this is completely linear, I would say. And that's typically what one sees in these type of, let's say, error analysis. So far we're pretty happy with that, but we still have to take into account that the solar sail also heats up, and we have to do all the rest about the of the microstructural model, but people are working on that as we speak. That's everything from my side. Thanks.
Yeah, thanks a lot, Lars. I'm going to briefly present some results on addressing Objective 3 about the system architectures of the sailcraft, and I'm notably going to present results of the work Wishdon has done during her master's thesis. Yeah, so some basic assumptions regarding the mission statement and the mission goals. So we simply wanted to design a sailcraft based on aerographite, which can reach interstellar space and can accommodate a kilogram-sized Strawman payload. We used a fairly common methodology for generating alternatives for the space for the sailcraft using certain screening criteria such as technology maturity, etc. And ultimately, what we wanted to come up with is some more conservative designs or concepts for the sailcraft and a few more advanced or maybe some innovative, interesting designs which are different from currently existing sailcraft designs. So just to present a few of these sailcraft concepts, the most conservative one is really to take the Icarus sailcraft, which has already been flown, and to replace that, if I'm correct, like Mylar-based solar sail material by aerographite. So this was like fairly straightforward, and this is like the baseline we used in order to compare the performance. We also looked into synergies between the sail and other subsystems. So one idea was to use the aerographite sail at the same time as an antenna, and that might be possible by doping or injecting certain materials into aerographite, and it might even be possible with carbon nanotubes, for instance, and that might enable this kind of synergistic sail antenna design. Wishdon also came up with what she called the Zelish sail, which was inspired by a art form in Morocco, if I'm correct. But the idea here is really to use different thicknesses of aerographite and potentially different optical properties of these different elements of the aerographite sail in order to come up with designs where, for instance, instruments can be accommodated and distributed over the sail, and potentially maneuverability and attitude control can be simplified by just fine-tuning the mass distribution of the sail and its optical properties. Finally, the hollow sail. Okay, right, thanks. The hollow sphere sail, this is not new, and this has already been presented by René Heller et al. In 2020 in their paper. But here we looked into which technologies could be used in order to integrate all the remaining subsystems into the sail, and which then proposed to you, for instance, like beta voltaics, which could be put at the center of the sail or even be put on the surface, and different like flexible electronics and printable electronics, which could be distributed on the surface of the sail. Finally, Scholze came up with a design of using a staged sail. Because aerographite has temperature limitations, so it tends to start melting or disintegrating at like 400 degrees Celsius. The idea is to use a highly reflective sail and a more temperature tolerant sail as a first stage, and then potentially to detach that sail and to use the aerographite sail in order to boost the spacecraft to its terminal or final velocity. We also started doing some trade space exploration by basically going through the different performance parameters and to see where are the potential sweet spots for each of these concepts. Now, the conclusions and next steps. To summarize, we have achieved some first computational mechanics results. Aerographite sail model was developed and first simulations were run, and we have developed some first sailcraft concepts which can accommodate a kilogram-sized payloads, and we developed some conservative and advanced designs for that. Conclusions. So we don't have a lot of conclusions, but at the moment we haven't identified any showstoppers. Hopefully it remains that way. But for the next steps, we are going to run further computational mechanics simulations, and we'll expand the range of models in order to in the end get to the point where we can really assess the feasibility of certain sail designs, and to evaluate quantitatively those sailcraft concepts presented before, and really exploring the trade space or design space of these different sailcraft concepts. And ultimately, what we would like to achieve is to really converge between the computational mechanics simulations and the sailcraft concepts, and really to perform integrated simulations of both. And with that, hopefully one day we are going to fly to interstellar objects and other stars by using these aerographite sails. Thank you very much for your attention.
Thank you, Andreas. Great stuff. You guys are making good progress. Thank you for all the hard work of you and your team. Keeping us on schedule, moving right on ahead. Next up we have Charles Chase. And by the way, for the folks that are attending on YouTube and the panelists, sorry, the webinar attendees, a reminder, we'll do Q&A at the end of all 4 talks to try and keep everything streamlined. So next up, we have Charles Chase giving us a talk for his team, consisting of Unlab, Technion, Israel Institute of Technology, UCLA. Title of his project is Asymmetric Potential Vacuum Fluctuations Force Experiments. So with that, Charles, you have the con, and I'll give you a 3-minute beep when the time comes.
Okay. Can you all see my screen okay?
We see you, we hear you. You're good.
Okay, good. Yeah, so as Sunny mentioned, the team here is Professor Dagan from Technion. And then Professor Jim Jimjeski from UCLA, and then handling the fab work for us is Ami from App Nano. They're a company up in Silicon Valley, up in Mountain View. And so we're working on trying to leverage the obsequious fluctuations that are going on around us all the time. And, you know, they go by a lot of different names. I prefer vacuum fluctuations, but the quantum vacuum, the continuum, 0-point energy, they're really everywhere in our physics and science, these fluctuations. From the ground state of the quantum harmonic oscillator You can't get below that ground state. In looking at black bodies and Planck's law, there is again the vacuum energy, which is always there at every temperature. And in fact, at room temperature above 7 terahertz frequencies, the vacuum fluctuations, this term here, dominates over the thermal fluctuations. So they actually have more energy at that point. And of course, there's the Casimir force, which causes objects to come together, be attracted to each other. The rationale behind that is that modes from the vacuum are excluded in between the plates, causing a pressure, just kind of like a boat near a dock when you don't have the waves in between the boat and the dock. They cause collapse. And that actually can be a very large force, as predicted, up to an atmosphere of 10 for a 10 nanometer plate separation. And in QCD, 99% of a proton's mass is from vacuum fluctuations, so mass by itself. And there's, as I said, these vacuum fluctuations are everywhere, driving spontaneous emission forces like the Casimir force, the Lamb shift, noise, generating photons, the magnetic moment of the electron, bound in continuum states. When people talk about the continuum, that's the vacuum fluctuations. So, but the question is, can we actually use these fluctuations for generating forces? And we think that you can, and our predictions show that you should be able to generate a force when you interact with either asymmetric potentials or asymmetric structures. In other words, you're breaking the symmetry of the vacuum fluctuations, and from the broken symmetry, you can generate a force. And so what's shown here is the very basic calculation of the wave function, the quantum wave function in an asymmetric potential situation, where you have an asymmetry situation, and then you have tunneling going through this barrier here. And as you can see, the wave function is different on one side versus the other side. And because of that difference, there in conservation of momentum, there has to be a force. And these type of structures are made in resonant tunneling diodes. Here's just one example here of a group out of Japan that made a large array of resonant tunneling diodes that have this tunneling effect. And our prediction is that you will generate a force that is perpendicular to the orientation of this diode here. And so that would enable propellantless propulsion. You are putting a current in to maintain the potential in the diode, but you're not using any propellant. And there's nothing to limit what speed you will get to. So it would enable acceleration to near light speed, only limited by friction from the vacuum itself. And here I'm just showing a little more sophisticated calculation, comparing symmetric structures to asymmetric structures. Again, this is the wave function. And on the top is a symmetric structure. And waves are incident in this case in both directions. So going to this direction and that direction. And with an asymmetric situation, you could see that the wave function, here the red is the tunneling, is the same on both sides. No force will be encountered here. But here we have an asymmetric situation. And again, looking at the tunneling, the red, you could see that the wave function is different on one side versus the other, indicating that there must be a force there because conservation of momentum requires that there be a force. Now, what we're relying on is the vacuum coupling to the tunneling current. And, and so if you look at the uncertainty principle above a certain frequency, the lifetime of what people call virtual particles, which is just a terrible name because these particles actually do exist for a certain amount of time. And they do come in and out of existence. They're real particles, although they're considered off shell versus on shell. The lifetime based on the uncertainty principle is longer than the tunneling time. So there's no reason why they shouldn't couple. And if you look at the literature, here's some recent results from literature. Can you actually do this? Can forces be generated from asymmetric vacuum fluctuations? And so a couple of interesting results, one using the dynamical Casimir effect. This is where you're having a time varying situation that generates vacuum fluctuations. And this is the group out of Baylor. And as you see here, we have seen an otherwise stationary object gain momentum out of seemingly nothing due to its interaction with the vacuum. And then this gentleman out of France, looking at a 2-atom system, has shown that a non-zero vacuum momentum and hence a non-vanishing total force would be found in any asymmetrically excited system. Which is what we have, is an asymmetric system. And then this group out of Brazil, motion induced by asymmetric excitation of the quantum vacuum, where they state a static object isolated from everything and just interacting with the quantum vacuum gets in motion by exciting the vacuum. They're using a time-dependent system. So, those are all theoretical, but there's also, and I've shown before, some of the work experimentally showing the vacuum through interaction with it. And this is a recent paper out of Marin's group at MIT, working with Giannopoulos, where they're showing that with the quantum vacuum, they can bias probability distributions so that you put them on one side of the probability or the other side of the probability by the interaction with the vacuum. And they have test data showing that this actually happens. So again, indication that yes, you can interact with the vacuum, and theoretically, yes, the asymmetric situation will generate a force. And these are our calculations from before. Looking at the resonant tunneling diode, that example that I showed you there previously that the Japanese group made, by using the fields that are inside this diode, we show that each diode will generate a small amount of force, about 2.3 piconewtons. But when you look at a total array, say on a wafer, and you take the typical size, 10% coverage, you can get 9.3 newtons per kilogram. That is almost launch forces, enough to get up to orbit. So, pretty amazing capability, maybe, possibly. And we've extended the analysis. This is work from Yuval, where we're taking a look at asymmetric dielectric structures. So this does not have a current input, but it provides asymmetry by the change in the dielectric constant. And so here's the model here, is you have a low dielectric material and a high dielectric material separated by a vacuum. And and then by taking into account the fields in both directions, we show that there should be a force in a particular direction. And if you think about it, what we're doing is we're exciting the modes in these different dielectric materials are different. And the vacuum is exciting the different modes. And so there'll be different excitations in the low dielectric versus the high dielectric, leading to an asymmetric situation where you get a force. And similar to our diode calculations using the Maxwell stress tensor, you're able to calculate what the force is. and this is, the same sort of approach gives you the Casimir force, and, it's a well-known technique. And what you see here is mapped out as a function of the differing here index of refraction or dielectric constant of the two materials that are separated by the vacuum. And what's being plotted is the force normalized to the Casimir force. So 0 here would be the Casimir force in color. And when the dielectrics are the same, you get just the Casimir force. But if you have a difference, you're getting definitely getting a I should say you're getting a 0 force at along this dotted line here. But as you have different dielectrics, you're getting forces that are actually larger than the Casimir force. And so we're going to go off, and test some of these geometries. We have defined our test situation, what we're going to be testing. We're using an atomic force microscope cantilever, where we're going to be looking at the deflection of a cantilever. And we're making the sample as large as we can. So this sample, which will be the asymmetric dielectrics or the asymmetric cavities, is going to be 500 microns by 500 microns. We're trying to make the force as large as possible. A conservative force prediction is about 10 piconewtons, which is very readily measured in our experiment. Could be as high as a nanonewton, which would be, really fantastic. So we've designed the cantilever, and we've made our final material selections of all the different variations that we're going to test. We're going to be testing a symmetric cavity as a baseline. Then we're going to be testing asymmetric cavities, and I'll show you pictures of these. Then an asymmetric dielectric constant. And then based on the analysis that I just showed, asymmetric dielectric constants with a cavity in the middle, and different variations of each one, so that we can, make sure we're about what we're measuring. And each configuration is going to be measured as a function of orientation, and then also at different temperatures. And so the symmetric cavity is going to be a silicon oxide separated by metal. Here's the giant cantilever in relation to the sample itself, different cavity dimensions. The asymmetric cavities are the same material, but where we have the thickness of the cavity is different, and we should be getting a force out of these, we're predicting. And then the asymmetric dielectric constant, again, silicon oxide and titanium dioxide, which has a very high dielectric constant, again, with different cavity geometries. And then this is the one representing our recent calculations, where we have a low dielectric, and then can't do a vacuum in between, but we're going to use magnesium fluoride, which has a 1.9, and then again titanium dioxide on this side. And to maximize the force in this situation, we like the ratio of D over A to be small, but we also want A to be small as well. And so that's why you see these very low, these very small geometries here. 10 nanometers with different size cavities. So, oops. Okay, I'm not sure why if everyone is seeing this double sort of thing, but so we've initiated fabrication of these. We've defined the process flow of how these are going to be made, and we've started laying out the masks. And so we're going to be building these structures like the ones that I showed you. And then, just to remind everybody, the Casimir forces measure attractive and effective repulsive forces. but they don't measure motive forces. As far as we know, no one has tried to measure motion caused from the vacuum fluctuations. That's a new type of measurement, hasn't been done before. And so Professor Jim Jimjeski at UCLA is going to be doing these tests for us using his low temperature AFM that's in his lab here. Beautiful machine, ultra high vacuum, very sensitive. And, you know, the idea of these paddles with the sample, and again, we're going to have very large samples, 500 microns to 500 microns. Cantilevers on the order of 750 microns. And then the samples will be placeable and removable, so we'll be able to flip them upside down, test them in both directions. And then using a fib, we'll be able to drill little holes in the end of the cantilever so we can change the resonance to optimize it for the amount of forces that we're measuring. And I think, I'm not sure, it's about the amount of time I have, I think, but I think Jim is online, but as
you got 3 more minutes, Charles.
Okay, all right. I think Jim is online, but as a guest, not as a panelist. I'm not sure. Is he able to talk or not? Sonny?
Yeah, give me just a second. I'm going to promote Jim to a panelist.
Okay.
Okay, wait a minute. Can you hear me?
Yeah. Hey, Jim.
Hi.
I didn't mean to put you on the spot, but I don't know if you had any
no
comments
problem.
about the
I mean, we
experiment.
only have a couple of minutes, but basically, what we're going to use are extremely soft cantilevers, and to achieve in a vertical vertical orientation, and at the base of the cantilever, we will actually cut a small slot to modify the force constant. I was in Bristol actually talking to some people in the physics department there, so that we think we can get down to about 10⁻⁶ Newton meters. And to put that into perspective, a regular AFM that studies biological samples is around about 10⁻⁻⁴ Newton meters. So even with the smaller force, we will still get a significant deflection. And we will study a number of samples where we change the orientation of the actual heterostructure. So the thrust will be in one direction, and in the other case in another, and a neutral one. And by separating the paddle from the cantilever, we will also reduce potential things like stresses. But the experiment is fundamentally different from regular experiments because the force is constantly acting irrespective of the actual orientation of the device. It's not like a magnetic force. And we have all that in place. So AMI will make these structures using silicon nitride, extremely flexible. And we can actually expect quite massive deflections with such a low force constant system. There is also a small piece of metallization for laser reflection, although we can also use interferometry if we want. I think is that sufficient, Charles?
Yeah, no, that's great. Thank you, Jim.
Yeah, welcome.
Yeah, and so that's where we're at.
Yeah. And I'm really excited. And we also have some stuff that we think is patentable if we can, a type of motor that's patentable if we are successful with these initial experiments to prove this is a concept. But it's a kind of revolutionary concept because this can change the world if we can actually extract energy from anywhere. Okay, the 0 point energy.
Very
Yep.
exciting. Yeah, awesome stuff, Charles and James. Really appreciate your guys' talk today. I think I saw that Phil had his hand raised. Phil, we will have a facilitated Q&A at the end of the first 4 talks, if that's okay. Okay. So pressing right ahead, next up we have Richard Nortke from Delft University of Technology over in the Netherlands. The title of his talk is Real Acceleration and Impulse Limits of Light Sails. So Richard, you have the con, and I'll give you the little 3-minute warning when the time comes.
Okay.
We've got your slide.
Can you see is it the right view?
Yes,
Or
we
is
have
it
the presentation.
Okay, so you see the presentation.
Mhm.
Okay, great. All right. Yeah, thanks for having me. So here I just wanted to a little bit update on the work that we're doing here at Delft in the Netherlands. And so one of the things that we're looking at is laser sails and what are the real limits to these kind of sails, both from a practical experimental standpoint, but also from a theoretical standpoint. So I maybe don't need to mention this too much here, but you know, a lot of the inspiration here is coming from the Breakthrough Starshot initiative. The idea being that if we can make ultralight sails, which are meters in size and really 1 gram scale, that with high-powered lasers we can push these kind of sails with microchip satellites out to Alpha Centauri in 20 years rather than 10,000 years that we're normally looking at. So really trying to get to speeds on the order of 1/5 of the speed of light with about 10 minutes of laser exposure. Just to give a quick sense of what the mission looks like, the idea is really to minimize the payload to a microchip, something that has cameras, communication systems, batteries, magnetometers, things that you would normally find on a spacecraft, but just really miniaturized and attach it to a large sail, which is 4 by 4 meters. Right now is kind of the idea. And the idea would be that all of this should be really on the order of the gram scale. And this just kind of gives you the critical density aerial density you would need to get to a gram scale. And so just to give people a sense, you know, we're really talking about something 4 meters by 4 meters that essentially has less mass than a penny. And so it really gives you a sense of kind of the real technological leaps that we will have to make in order to make this work. And so, one of the things that we're working on at Delft is really the sail, and we find that this is really quite interesting because if you look at what's involved in this really large project, you know, the microchip really has to do with miniaturizing everything in every dimension, X, Y, and Z. And the sail is really this kind of unique challenge where you really need to make it large scale, meter scale in 2 dimensions, but then keep its nanoscale thickness, and then also patterning it with nanoscale features, which really makes it very different than any material that we really know of or can fabricate, at least at this scale. If we look at kind of the top contender for some of these laser sails, what we're looking at is silicon nitride membranes, which are kind of a classic CMOS material. And it's pretty simple idea, which is that you have a thin membrane of this material, and if we can puncture it with holes, we can kind of counterintuitively make it very reflective. Essentially, these holes make it into a very reflective metamaterial. So this is essentially a little rendering of what such a mirror would look like, and this kind of gives you a sense of how the reflectivity works without the hole, without holes, just the bare membrane. We have about a 30% reflectivity across the scale, across the range, the wavelength range. But with this patterning of small holes, we can get this very high reflectivity at a very specific wavelength. So here the idea is being that the light comes in, a mode is excited in the membrane, and this mode constructively interferes with the incoming beam and destructively interferes with everything passing through. And so we essentially have a mirror made out of one singular layer. And just to give you a sense of why silicon nitride, you know, people have really looked at a lot of different materials. So if you look at the Keros solar sail, it's the polyamide film with some reflective metal layer to make it reflective. This is what a distributed Bragg mirror it looks like for conventional mirrors, and a silicon nitride mirror for photonic crystal mirror is really one layer that is completely punctured in holes, small nano holes. And so one of the things that silicon nitride does for us is that it really actually spans a lot of the requirements that we need for Starshot, right? So we need to be able to make it at, let's say, even minimally centimeter scales. This has only been shown in silicon nitride. Getting the reflectivity up to 90% at this critical areal density is also something that's really been shown in silicon nitride. And that it has actual parts per million absorption, doesn't wrinkle, and is amorphous. So all of these things are I would say somewhat very much needed to get to the targets of Starshot's ambitions. So just to give you a sense of where we're at, what the state of the art looks like. So this is essentially what an SEM of one of these silicon nitride membranes. If we zoom out, you can see that these membranes are really filled with holes, completely covered in holes. What's blue here is suspended membrane, and purple is what's attached to the wafer. If we zoom out, we can zoom out, and these are more or less kind of the conventional sizes of silicon nitride reflectors that have been usually made for optomechanics. And so this is something that I've shown before, but one of the things that we were trying to figure out is, can we actually make these things larger? So now this is what I was showing you here, what is kind of the conventional size of these reflectors, and now we can make them around 16,000 times larger. And one of the things to say here that's very important is that because of the way that we do the lithography here, the lithography just on this sail costs somewhere on the order of about I would say $30,000 here just to make one sail. So this is something that we really wanted to start to look at, amongst other things. So one of my students, Lucas Norder, has been essentially looking at acceleration distances and what kind of actual designs we can use to get a smaller acceleration distance. So he's been using some mixture of neural network optimization and topology optimization, which are usually kind of two different fields. And he's been using this to try to redesign sails. And one of the questions that we had was, you know, can you actually accelerate sails as fast as you want? We always have this optimization of let's get this thing to go as fast as possible. But one of the very important questions is, what can a sail made out of the strongest materials which we have, what kind of actual strains can it take? So right now, what a lot of the reflectors are using are either something that looks like a square lattice or hexagonal lattice of holes. And what his simulations are finding when we start to look at costs is that we can start to get these new type of configurations that look somewhat like a pentagonal lattice. So just to give you a sense, these are now some of the new sails that we just made in the last few weeks. So you can see they're significantly bigger. So two hands here holding, just to give you a sense. This is the outline of the sail that we're making now. So now we're making them on the order of 6 by 6 centimeters. But what I think is really important here, which we're really happy about, is that we've now, with the new design of the photonic crystal, we can now make feature sizes that are much bigger. And this allows us to actually produce these sails at about 10,000 times cheaper cost. So now, you know, we were talking about lithography that costs tens of thousands of dollars to do, and now we can get this down to, you know, hundreds. And so just to give you a sense of how we design these sails. So this is just to give you a picture of a broken sail. So here you see that what we did was we tried to make different sections of the lithography which overlapped, and this can cause tearing as you get overlap of holes and kind of sharp corners. So what we started to do was to implement new strategies where, for instance, we could make kind of like a subframe or a missing row of holes, which gave it a little bit more stability, but also avoided any issues with stitching from the lithography. So this is essentially what our new sails look like. So this is this pentagonal lattice this is a real microscope image, and you can see that we've started now to try to also implement the same strategies. And just to show you that not everything works all the time, this is a picture of the sail when we try to suspend it. So we can now, you can see that, yeah, it's really broken here. And one of the things is, while this may be very sad, I think what made me personally happy was that we now made this so cheap that we didn't have to worry about, you know, the $58,000 this would have cost if we had done this with our old method. So this is something where we're really happy that now, by driving down the costs of our sail production, we don't have to worry about these kind of breakings if they do happen. And that's really something, because I think that allows us to really get creative, take some risks, and innovate a little bit here. So I think this is something where we're really quite happy that we can continuously try to make more sails, try to really increase the sizes and really go much further. And so maybe one of the things that I first spoke about was not just the cost, but really the destructive forces on these sails as you accelerate them. And this is something that we just wanted to, for our own curiosity, we were trying to figure out, is there a real fundamental limit to how fast you can accelerate something or a real sail material before it breaks? So one of the things we looked at was just a continuous silicon nitride film without any holes as kind of a max estimate. And I actually found it very interesting, this talk earlier with the pressures on the sails, because we also ended up getting, if we started off with a flat sail and put a uniform pressure, we would also get these very, very large displacements, like something on the kilometers, and which we thought maybe was not really something realistic, but we weren't sure. So we started trying different ways of simulating this, and we started to get what we think are maybe a little bit more smaller displacements that we think a membrane would make, so something on the order of millimeters. But even when you look at, for instance, the pressures that you would feel from a 10 gigawatt laser that's now being planned for Starshot, we would get tensile stresses on the order of about 138 megapascals, which is actually really good. That's actually far below the fracture strength of silicon nitride, which is usually on the order of gigapascals. And so one of the questions for us was, okay, so how can you actually push this? So this is something that we've been also working on, the simulations, to see what pressures or what laser powers would you need to get to in order to get stresses in the middle that are now starting to line up with the fracture strength of silicon nitride. And again, this is a max, kind of giving you a max estimate, because it's a uniform film. Whereas if we puncture it with holes, with billions and billions of holes, then you're going to start talking about a very different, more fragile material, although much more reflective. So we started looking at essentially what is the actual effective Young's modulus, let's say, all the effective. So what we want to do is we want to essentially find out what are the effective material properties of a silicon nitride sail, so that we can start to topology optimize the entire sail. So for instance, here, if you look at a sail with a radius of 5 microns, which is really tiny, you start to see we start to try to calculate these effective Young's modulus. And so as you go to bigger and bigger radii, where the holes become more and more kind of homogeneous, and it really becomes a true metamaterial, you start to kind of see the effective Young's modulus start to kind of plateau. So to something we can use. And just to round things up here, so this is where we're at. So we've really got full simulations of what the sails look like on a uniform scale, trying to get these things to give us values that we think a sail could actually deflect, and kind of getting them to also to line up with analytics. But we also started thinking about how do we go faster. And so one thing that we're starting to look at now, which is going to be a little bit more of a challenge, is not just having uniform holes, but really having holes that change from the center to the edge. And this is both from the optical perspective and also from the perspective of making a sail that, for instance, is less susceptible to breaking at critical points. One of the things that we've done, actually, which I'm really happy about with the support from LSI, is that we were also looking at new materials and trying to see whether we can find materials outside of silicon nitride which actually have higher fracture strengths. And so what we ended up finding was we ended up finding actual very strong silicon carbide materials, which are now more or less giving us kind of the same fracture strengths that people are finding in graphene experimentally. And so this, I think, is really going to allow one to push the sails much harder than you would with a silicon nitride structure. So I think this will ultimately kind of bring down the acceleration distances we can get. So that's the idea here now. So practically now we're trying to really figure out how to bring down the cost of sail materials by really many orders of magnitude, so that we can really innovate here. The other thing is really trying to find the limits of acceleration distance. How fast can we really go before rupturing such a structure? And then how do we use machine learning and topology optimization to go beyond the traditional sail geometries, and then we're also really looking at new materials and design for maximizing performance. So yeah, I think I'll end there. So, thanks.
Thank you, Richard. Really appreciate you giving us an update on your guys' work. It's always neat to see the progress that you make, and it was. I really like the chart that you provided showing the much larger sail that you guys have managed to achieve. And so just before we go on, the one chart where you showed 58,000 with the damaged wafer, right? You were saying it did not cost you that much to do that based on these new directions. So it was what, 2 orders of magnitude less?
Yeah.
Okay.
Yeah. Yeah, because now what we're doing is we're using projection. We can now go to projection lithography, which allows us to write, millions of holes in 8 seconds rather than many days with a very expensive tool. Yeah.
Gotcha. Cool. Thank you. Awesome. Yeah. Thank you, Richard. Appreciate it.
Yeah.
Let's see. Continuing right on. This is the last talk for the morning session, and then we'll have some opportunities for some Q&A from the panelists and folks online. Next up, we have Kirill Zatrimilov and Remo Garantini from University of Bergamo, Italy. Kirill will be giving us a presentation titled Traversable Wormholes and Warp Drive, A Road to Interstellar Exploration. So, Kirill, you have the con, sir, and I'll give you a verbal warning when we get to the 3-minute mark at the end of your window.
Okay, so the topic of my talk is on the wormhole warp drive correspondence. First of all, let me begin with the definition of the warp drive. Warp drive is a particular type of solutions in general relativity. It's a solitonic bubble. It's a soliton-like bubble. Yes.
Kirill, excuse me, but there is nothing on the. Okay, thanks.
So that propagates in space. So generally, it's given by a metric of this form. This beta is a velocity vector, where v in is the velocity of the warp drive propagation. F is a function that describes the position of warp drive in space. Usually shaped like a step function, so it's 1 inside the bubble and 0 outside. And V out is the background is the background curvature of the metric. So this the observers inside the bubble are so while they are moving along with the bubble, locally they are at rest in an inertial reference frame. That's the key point. So a warp drive doesn't need energy to accelerate like the usual spacecrafts. So the best analog for a warp drive would be a boat moving along a current. So it's in general, if a boat has no velocity of its own, it's just flowing along the current in a normal gravitational free fall. And the starting point for our particular model is an idea proposed by Homer Edlis in 2004. So if we start with a Schwarzschild metric describing a black hole, then we can switch to a different set of coordinates to get a metric which looks exactly like a warp drive type metric. So this V out, this background velocity vector background flow is corresponds to this, and now this form makes it possible to embed an actual warp drive against a black hole background in this fashion. It was shown by Edlis. And in this way, warp drives can traverse black hole horizons back and forth in a way that's impossible for ordinary spacecrafts. Now, our idea was to generalize this to a Morris-Thorne wormhole. So without loss of generality, spherical asymmetric metric can be written in this form. And in order for it to be a wormhole, we remove a part of space which is smaller than a given radius r. This is called the throat, and glue it together with another part of space-time in which this region has also been removed. So the radius changes from plus infinity to r, and then from again from r to plus infinity. These two regions are not identified. They may be in different universes or in the same universe. And for this metric, we can perform a similar transformation to obtain a similar metric. But here we get, in front of the r, we get an additional form factor, g of r, which makes it a bit different from the ordinary warp drive metric. And this form factor has this form, and now we can still follow the same procedure to embed the warp drive, and then in order for the wormhole to be traversable, we have to satisfy the flare out condition, then the throat condition. So B has to become equal to r at the throat, this has to be, the denominator here has to become 0. And the absence of horizon condition means that the prefactor in front of dt square cannot become 0. So taken together, if this is never 0 and this is 0 at the throat, it means that the form factor is singular at the throat. Normally for a wormhole, it's not an issue because we can introduce the so-called proper length dl equal to dr divided by a square root of this, and then then this expression is integrable, and so this singularity is a purely coordinate singularity. However, once we do this embedding, the situation may change, and we have shown that it does indeed change. So if we compute the Ricci scalar for this type of metric, it can be, first of all, we write it in the spherical coordinates in this form, and then if we compute the Ricci scalar, we see that it has this form. So j cube in the denominator, and then g prime squares, because it's 1 over square root, and g prime is 1 over 3/2. So it squares like g cube. G prime prime squares like 5/2. So g to the 5th power, and so it means that in the Ricci scalar we have quite a number of divergent terms. And so unless this function f, which describes the warp drive, unless it's 0, so we have no warp drive at all. It's impossible to set all of these coefficients to 0. So we reach a paradoxical conclusion. So a warp drive can traverse a horizon without problems, but if it encounters a humanly traversable wormhole without a horizon, then it would see a real singularity when approaching it. We still have, it's for the time being, it's still a preliminary result. We still have to check a number of things for our paper on the topic, but for now, our conclusion is this. Now, both warp drives and wormholes are hypothetical objects at the moment. We have only seen black holes. So what should be the takeaway from this, from the engineering point of view? A Canadian physicist, William Monroe, proposed in 1981 that physical gravitational systems could be simulated with barotropic rotational fluids. So the equations of the Eulerian equations of motion for the fluid, if under a certain condition, they can imitate the equations of motion in general relativity. So, so if we write the equation for the velocity potential of the fluid, the perturbation of the velocity potential, then it looks exactly like the wave equation for a scalar field, and the effective metric there would be this one, which this is the background fluid density, which is considered constant, and this is the and c is the speed of sound in the fluid, and so we get, in this way we get a metric which is exactly the warp drive metric given there. So this is exactly this. There have already been, so if we do a similar coordinate transformation, then we can map it to this, which for a specific choice of the radial velocity profile, it gives us a Schwarzschild metric. And this was already done experimentally by a group of researchers from Israel who took one-dimensional Bose-Einstein condensate rubidium atoms and demonstrated that one can, so like if there is a region in which the flow is subsonic and another region in which it's supersonic, then between these regions we have an analog horizon, and they have been able to observe the analog Hawking radiation from it. In principle, we can add them. So there have been also analog models proposed for warp drives. So in principle, we can combine and we can modulate. So we have this, again, we have this background velocity profile corresponding to a black hole, where here it's subsonic and here it's supersonic. And then we can have a velocity perturbation, a wave moving at a given speed. So it's moving from the subsonic region to the supersonic region. And that would be the analog of the warp drive in this case. But now, if we want to do a wormhole analog, this is more involved because we cannot simulate the topology in analog systems because there is no way to connect to disjointed systems. But we can still try to simulate the behavior near the throat. So the Morris-Thorne metric without the removal of the inner region. For this purpose, so as the analog metric is this, then in order to get something other than the Schwarzschild out of it, since we have two independent functions here, the prefactor in front of dt square and the prefactor in front of the r square, then in order to physically realize them, we need additional degrees of freedom. So we need to modulate the speed of sound. We need to make it very A in space. So it's once we make it a function, we can by identifying it with this with exactly this form factor, we can regain the Morris-Thorne metric there. So, and interestingly, the most problematic thing would be to simulate the a traversable wormhole, because in this case, this form factor would become infinite, and the speed of sound would also have to be infinite. Otherwise, when we have a wormhole with a horizon, we should be able to simulate it and in a similar procedure run a wave on this background to see how it traverses a horizon and what happens physically. So the conclusion is the following: we have found a generalization of the coordinate transformation for black hole that maps a wormhole metric to a certain type of warp drive metric. However, we encounter a potential problem that warp drives may not be able to traverse traversable wormholes, but only wormholes with horizons. This is to be confirmed. For now, this is a tentative result. Then our research may also have some relation to the ER-EPR correspondence. So the idea of ER-EPR is that ER stands for Einstein-Rosen, which is the Einstein-Rosen bridge wormhole, and DPR stands for Einstein-Podolsky-Rosen, which is entangled particles. So the idea behind this is that special entangled that two objects, two particles which are entangled in the quantum wake are actually connected by a wormhole. And then if if tiny warp drives can traverse the horizons to travel between them, then in principle it could be a physical mechanism for realizing the APR correlations. However, so far our computation has been purely classical, so we have to see how these warp drives would interact with the quantum fields, and in particular with the Hawking radiation, because in order to realize the APR correlation, the warp drives would have to be superluminal. This means they would have a horizon of their own, and so more work needs to be done on this. And finally, we propose that these kinds of systems could be physically realized, and we could at least qualitatively study their properties with analog gravity setups. Thanks for your attention.
Thank you, Kirill. Appreciate it. Very thought-provoking presentation, and lots of interesting things you're thinking about. I really like some of the summaries here on this slide. Some of the things that you're taking away from some of the things you're thinking about. So now we're getting to a point where we can go back and take some questions for the four previous presentations. Kirill, if you could stop sharing your desktop, that'd be great. So I think I recall that Phil had his hand up, and he's got his hand back up again. So Phil, you get the microphone first. As part of the questions, tell me who the question is for, and then the question.
Okay. Thanks, everybody. Great presentations. Always a joy to be on these reviews. This is for Charles and I think others involved in the general idea of extraction from the vacuum. Okay, and a great talk, Charles. Just wanted to say thank you. It was very very clear. So the general question is more or less as follows: how does one extract at a distance rather than at microscopic scale? So the question could be similarly thought of as if I say I have two protons and I ask what is the force on each proton when they're very close together. I would conclude that there's an enormous force on the protons per unit mass. But then I realized that that doesn't really work because the further away I go, the less force I have. So the question for you is, you're dealing with microscopic elements. How does it scale to macroscopic elements? So for example, you quoted about 9.3 newtons per kilogram. So close to 1 G for a kilogram on the surface there. But I don't think that would scale so that you could actually launch something. Could you address the general issue of force at a distance?
Yes, so I think the way I view it is that is the force from our asymmetric, our resonant tunneling diodes that are formed as an array, and that's it's constantly pushing, it's constantly moving the vacuum in the one preferential direction. So there's as conservation of momentum, there's going to be momentum of the vacuum moving in one direction, and then the object better move in the other direction. And I view this thing as distance as like a time thing. So in other words, that the vacuum fluctuations need to be in existence long enough so that they can tunnel through, and couple to a tunneling resonance. And so when I think of distance, I'm not really thinking of it in the terms that you are. So maybe I don't quite fully grasp the implications.
I think it's everywhere, right? So
Yeah.
it's not, there is no distance in that sense. I mean, we're surrounded by we're surrounded by it. So it doesn't matter where you are, presumably, maybe, I don't know, in another part of the universe if it changes, but not to my knowledge. So it's not at, it's not at a distance, you see.
Well, I get that general idea that, obviously that we think of the vacuum as being everywhere, that I understand. I think it's the question of how one actualizes a macroscopic object moving. So if on the desktop you were to show that, you had a small object and it's zooming across the desktop, without any seemingly external power.
Yeah.
So if you could just kind of run us through how you would, I get the general idea.
I think you have to think. This is a small device. So you've heard about the solar cells before and so on. So you can imagine, a system where we have many of these cells. They can be also, stacked up, and the force is constant, so the acceleration is constant. Maybe it needs something to get it started, I mean, we're not going to get into orbit, but if it's in space, then once it's in space, it's just like a gradual acceleration, and
You might need a break.
we do have, well, we have some material, we have some stuff, but that's something that we can't discuss here, on how you would actually do that in space. However, I think the point of the experiment at the moment is just to show that indeed, if you can extract energy from the vacuum, it has more implications than even space itself. And this is our initial heterostructures. So what type of heterostructure we can create in the future using, more, clearly we need a lot more money, is dependent on these initial experiments with the cantilevers. So the embodiment, like a motor, we do have, we have already plans for a motor on phase 2 if we get to phase 2.
I think we have a question from Lyndon Zinsky as well.
Thanks, Sonny. So my question was related to Charles. So if you're harvesting a force from the quantum vacuum, have you thought about how you might control that? It seems like it's always on, right? So how would you mentioned a moment ago, how would you brake? How would you steer? Have you given some thought on a practical level on how you might do those kind of things?
Yeah, so you'd probably want devices in different orientations, and maybe something that you can rotate and move. Because otherwise you just keep accelerating to light speed, right? And so maybe you don't always want that, or you want to slow down at some point. So you have to be able to orient the devices.
If you have 4 cells and 2 of them are in opposition, it won't move. And if you turn them, you get twice the thrust forward. That's
right.
Yeah.
Thank you.
What other kind of questions we got? I do have a question from YouTube. This one's for Remo and Kirill, and it's a simple question on the nature of wormholes. It says, it's from Steffi Rucco. Can a traversable wormhole be created to find shortcuts through space and time? Remo? Uh-oh. Looks like we have a connection problem. I'll answer the question for him. The idea of a wormhole or a space warp, these are 2 kind of loopholes in general relativity. General relativity has what I call the 11th commandment, thou shalt not exceed the speed of light. But that same mathematical framework says that space can expand and contract at any speed. And so there's some potential mathematical things that can be explored that lead to loopholes to get from one point to another that's very, very quick. And so a space warp is one mathematical solution. And then the idea of a wormhole is another. And so conceptually, a wormhole is a way to connect two different spaces that are very far apart in such a way so that you can go from here to Proxima Centauri in 2 weeks, for example, as measured by clocks on the spacecraft and as measured by clocks at mission control here in Houston. I don't know about time. I don't think that's, personally, I don't think that's possible, but it remains to be determined if a space warp or a wormhole is even possible. That's part of why we fund, we're funding Remo and Kirill to do some fundamental thinking on what the mathematics might be. So what else we got from the group here? So I think I have a question for Andreas, going back to your sales structure using aerographing. So you were talking about looking at things kind of at a very low level. Have you had a chance to kind of pull back to a higher level and think, all right, what would be a prototype at scale that I could make, kind of exploring this material in some form factor that I could do some stuff in the lab, and you know, how in your mind would that map to some potential CubeSat kinds of missions? You know, maybe you can speak to what are your, you know, your diabolical plans, if you will. Have you given some thought to that?
Yeah, great question. So at the moment, aerographite is manufactured in the lab at the size of maybe like I would say like centimeter scale structures, and what we could do with that in space is to have a setup where solar radiation basically pushes an aerographite sample, for example, out of a CubeSat and then into deep space. And in principle, that piece of aerographite should get to escape velocity and then they basically fly around in interplanetary space at some point. So of course, unfortunately, we cannot track that piece of aerographite, but I think that would be the lowest hanging fruit experiment to do something in space and to demonstrate that it works.
And what did you say the size of that? What was the size of that again?
Oh, it's like centimeter scale. I mean, those samples are like I would say maybe a little bit larger than a sugar cube.
Yeah. Okay. All right. Interesting. Yeah, that might be fun to think about. I guess on the same token about manufacturing, so Charles and Jim, you guys had talked about making some, I'm going to say like an atomic force microscope tip, but that's not exactly what it is. It's so specialized. What's in your mind? What's the time frame for you guys to get to a point where you can maybe have some of those tiny prototypes in your midst in the lab? I guess Charles had to step off maybe. Jim, are you still on? Jim Zimzewski? They may be having a sidebar conversation. So, okay. All right. Well, let me switch gears then. So, Richard, you know, in terms of the progress that you've made to date and the progress you have coming up, right? Sticking with this theme of what's a potential near-term mission you could potentially try and go after, say in the next 18 months? Is that even remotely possible?
Yeah, I think for us the main thing now is So right now what we're doing is constructing new setups so that we can make essentially small launches of centimeter scale light sails. So the idea really being to use a high powered laser and really try to lift these things in the lab and see if we can really stably lift them in a way that's controllable, that we don't burn them very quickly from the absorption. And that already, I think itself is going to be something really challenging, because if you look at optical levitation, essentially what we're doing here is in a way optical levitation against gravity. But if you look at what people have lifted with optical levitation, it's usually on the nanogram scale. And what we're wanting to lift is something on the milligram scale. So you're talking about something 100,000 times larger than what people have done before. But and so that's kind of right now on our radar. But again, one of the big things for us is that it has to be cheap, because if we blow apart one of these things, it can't cost us 50K each time we do it.
It could, but you wouldn't be there very long.
That exactly, yeah, exactly. So so for us, the cost is really one of the paramount things for us. And I think it's actually leading to very interesting designs. Aside from being a practical thing, it's actually leading to very interesting considerations.
Okay. All right, Charles, I see you're back. I had a question for you when you stepped off. Charles, can you hear me? Charles Chase, can you hear me? I guess not. Oh well, we'll catch him during the next Q&A. So let me open it back up to the panelists. Do we have any questions for anyone in the group of four?
Maybe I had a question. Actually, this is for Andreas, because we were actually looking like we were simulating very similar things with these sails and uniform pressures.
Andrew noted that.
Yeah, and so I was really wondering about this, because you guys showed that you have these 13-kilometer displacements, and we got something similar, and we thought, is there a material that will deform this much realistically? And I don't know how that. I know for silicon nitride I think it was a big no on our end, but we don't know how it works for your material. So I was very curious about this.
Yeah, I mean, also for aerographite, this is completely unrealistic. I mean, the reason why we get these values is because in reality, obviously, if we would integrate the microstructure of aerographite, then at a certain point it would simply disintegrate, and that's the reason why we get these values, but still from the simulation. But obviously, it doesn't make sense from if we would use the real material, it would simply fraction. It would like fraction, and if there's any material which could be displaced to that extent,
But do you think it's a real number, or do you think it's a simulation like glitch or something like this?
So it's not a numerical artifact, because Lars compared it to an analytical case. So and there was a correspondence.
Okay.
I think the reason for this is probably because the elasticity of the material is very large, but because it's like a, how would I say, like a network structure, I think without taking account the microstructure, there's really a decorrelation between the macro behavior and the micro behavior. So yeah, that's at least my explanation.
Okay. Yeah, I think it would be great to discuss, because we're literally just doing the exact same things almost, but for different material systems, but it would be interesting to compare to see if
definitely
yeah.
Great to see the interaction too between the teams here. That's awesome. What other kind of questions we have from the panel? I'd like to ask a question.
Okay.
Go ahead, Jim. Go ahead.
Yeah, no, I was just interested in you talked about the aero graphite. And my question was, how diamagnetic is it compared with, say, pyrolytic graphite? I'm just interested in it from the point of view of levitation, actually.
Yeah, I'm not entirely sure I understood the question, but whether aerographite would levitate?
Yeah, well, pyrolytic graphite is, very diamagnetic. It's extremely, I mean, one of the highest diamagnetic materials. And so I'm interested in how diamagnetic the aerographite is in comparison, say, to pyrolytic.
That's a good question. Actually, I don't know. And as far as the literature is concerned, I'm not sure that dielectric property was brought up. So I cannot respond to that.
Okay, thanks anyway. Yeah.
So, hey, Jim, since I have you back, I was trying to ask a question to you and Charles earlier. So don't run off. We got time for just another question. And it had to do with fabrication timelines for some of those, for lack of a better way of describing them, the customized atomic force microscope tips, if you will.
Mm-hmm.
What's the what's the time frame you think to be able to make some of those?
Well, Amy has been doing this forever. He actually started in it used to be, it was Vico, and Vico owned the company in Santa Barbara, and then he set up his own fab. So he would be the best person to ask, but in reality, it doesn't take very long. There's always the possibility that, they do it by the wafer, right? Yeah. So, I mean, there is a possibility that wafer gets screwed up, but when you consider the kind of dimensions we're talking about, and so on, I don't see a problem with that. And in terms of then the post treatment, that would be using the dual beam, the focused ion beam for the machining of the cantilever. We have that at CNSI in-house, so that's not a problem. And then the actual experiment itself, because we are using such soft cantilevers, it's not like we're going to be looking for, even a nanometer motion. We're more concerned with, tens, maybe even hundreds of nanometers if this thing works well. Yeah, I don't know if Charles is getting anything to add to that. The silicon nitride is a fairly standard material, and the deposition of the material on the paddles, he has all those materials available. Okay, so we can, it's not like we have to reinvent how to deposit those things at all. I would say it's a pretty standard thing, and the fact it's so big, I'm normally dealing with things that are, tiny, like some of the cantilevers in Bristol, they're like 200 nanometers thick, and that's pretty thin, Yeah,
I think I remember from your slides, you had the thinnest layer I remember seeing was 10 nanometers in terms of thickness that you're going to try and grow or deposit. And so, I mean, that's thin, but you can get thinner, right? So.
Oh yeah, we can get much thinner, but this particular machining is a very efficient way that, let's say we have, a bunch of cantilevers, right? And then we can make those, we can use the fib on the same cantilevers. Otherwise, if we had to actually make all the cantilevers different thicknesses and so on, that would just, it would cost a lot of money, because you have to make, different wafers, and it would also cost a lot of time. So we've kind of considered the way to do it in the most efficient manner. The design requirements, that was something that took the most time, and that's because Yuval, was doing these pretty complicated calculations, and no one has actually done a calculation in a proper calculation of the idea that you take something and this heterostructure, everybody's looking for forces inside it or between different elements, but nobody ever has considered the idea of the asymmetric thing, structure, which has a motive force in itself, which is independent of distance and so on. Anyway, yeah. So we're really excited, and it's great that the Limitless Space Institute are behind us. Because it's quite a radically different idea.
Good stuff. Yeah, thank you, Jim. I really appreciate you giving us some thoughts. So looking at the time frame, it's at 12:15 Central Time here in Houston. We have a scheduled break at -5 minutes. So what we'll do is let's go ahead and plan on doing a 20-minute break. Let folks step off, take care of a few things that they need to, and then we'll be back at 12:35. So if that's okay, we'll take a 20-minute break until 12:35, and then we'll start back after the break with Jeremy Bundy from University of California in Davis. So I'm going to leave the screen up and put a little PowerPoint slide up so that our friends that are online watching us on YouTube will know that we've stepped off. So see you guys in a few. All right, we're back here in Houston. Welcome back, everybody online that's watching us on YouTube. Getting started on the second half of the day. So next up, we have 5 of our grant winners coming to talk to us about a bunch of really awesome topics. The first one up we have is Jeremy Mundy from University of California, Davis. The title of his talk is called the Casimir Torque Thruster. Jeremy, you have a con, and I'll give you a 3-minute squeak when the time comes.
All right, sounds good. Thank you, Sonny. Can everybody see the screen okay?
Yes, we have it. We can see your screen, and it's in PowerPoint mode.
All right, perfect. Thank you so much. All right, great. So this concept that I'll be talking about, the Casimir torque thruster, it's kind of made up of 3 different sorts of components. And so I'll walk you through these 3 different concepts and how they can be combined into this torque thruster concept. So first is the Casimir effect, which we've heard a little bit about earlier, the Casimir torque, and then also something called the dynamic Casimir effect. And so kind of we can combine these together to get this torque thruster. Something else I'll also say, so this, the way that I think about this too is not really extraction of energy from the vacuum, but more of a conversion of energy from one form to another through the vacuum. But I'll kind of talk about that as we go through as well. All right, so starting off, how empty is space? So we heard about vacuum fluctuations earlier, and so we all know that even a piece of vacuum that appears fairly empty actually has lots going on in terms of vacuum fluctuations. And so the way that I like to think about that is basically starting off with electromagnetism and trying to apply quantum mechanics to it. So if we look at, for example, Maxwell's equations, we have these simple differential equations here. And we know the solutions to those classically. We can solve that, and we get these simple harmonic oscillator solutions. But we say, well, that's great, that's classical, but how does this work out quantum mechanically? And so when you have some sort of differential equation, you have simple harmonic oscillator solutions. When you treat that quantum mechanically, you basically have energy eigen solutions that look of this form, right? So the energy functions go as h bar omega, so Planck's constant, the frequency, and then we've got the stuff in parentheses. We've got some constant n here, which turns out to be either the photon number state or the number of photons, as well as this 1/2 here. And of course, if we're in what we consider the most empty of vacuums, we get rid of all the matter and all the photons. We're still left with a little bit of this energy, and we heard this referred to earlier, as well as the 0-point energy. And so the question is, what can we do with this energy? And that's a question that has been around for a while. And it turns out that there are a number of things that people have done. And so I'll first start off talking about the Casimir effect. And so this is also brought up earlier, but I'll just kind of go into a little bit more detail here. But so Hendrik Casimir was thinking about what happens when you confine the quantum fluctuations between 2 surfaces. So you can imagine these different waves here. These are the quantum fluctuations being confined. And he considered it for 2 different situations, one where the plates are very far apart and one where they're relatively close. And so clearly when they're very close together, you can fit fewer of these modes, fewer of these waves would fit inside here. And so there's a smaller energy density because you can't fit as many waves in there. So it's in a lower energy state, basically, when the plates are close together. And so you can look at the potential energy here, how it changes when you have the plates very far apart to when you bring them very close together. And so you see that has some distance dependence here, 1/distance 3rd power. And so since you have a potential energy here that has a distance dependence, you can take a derivative of that, and you can determine a force here, which goes as 1/distance 4th power. And then we have a bunch of constants, and it scales as the area of the plates. And so he concluded that there exists a force due to these quantum fluctuations that will pull these plates together. And this is back in 1948. And so does that really happen? Yes, it does. And there's a lot of experimental evidence now over many decades. In fact, within the first 10 years of his prediction, there were some early experiments that confirmed, at least within an order of magnitude or so, that you had this effect. And this kind of categorizes some of the types of experiments that have happened over the last several decades. So it's kind of a number of kind of confirmations of the Casimir force and advances in force measurement techniques. And we heard a little bit about AFMs as well earlier today. So AFMs were also used in some of the kind of late stage, early experiments here where they started getting fairly high resolution and high sensitivity. And then it went from just kind of measuring the Casimir force to being able to modify the Casimir force either through material properties or through geometries. Here are a few experiments we've been doing in my labs, looking at ways that we can use either geometry or materials in order to modify the Casimir force. So that's the Casimir force. So it was based on quantum fluctuations, predicted, experimentally confirmed. Casimir torque. So what if we have boundary conditions that are anisotropic now? So basically what we mean there is that with the metal plates, you are confining the modes, the electromagnetic fluctuations between the plates because they were metal and the fields had to go to zero. Now, if you have something that's optically anisotropic, you now have boundary conditions, again, that, whenever you have a wave that is impinging on the plate or field that is here, a boundary condition that now depends on what the orientation of these plates are. And so you can imagine that the total energy density that you have for all the different modes will now depend on the angular orientation between these two plates. And so this is also something that was predicted, that you would then have a torque similar to the way you have a force, but for isotropic materials. And so this was predicted again kind of in the mid 1970s by a couple of different groups. And so then in the last few years, this is something that we've also experimentally confirmed. And so here we're looking at basically this is what we call Casimir torque between birefringent plates in a liquid crystal, different types of birefringent plates, and you can see there's this kind of sine 2 theta dependence on the orientation, basically causing the plates to align to some energy minimum, kind of like you do with the forces as well. Okay, so that gives us our first two pieces. We have the Casimir force, we have Casimir torque, and now I'd like to mention this phenomenon called the dynamic Casimir effect. So for the dynamic Casimir effect, this is related to basically motion of objects relative to each other, giving rise to some sort of acceleration. There's a nice little cartoon here that I like that kind of describes this. So you can imagine you have your box, and let's say you want to close your box here. It's got quantum fluctuations all around it, and you want to shake up that box. So whenever you shake up your box, if you're in a classical world, you open your box and basically nothing has happened. But in a quantum world, what happens is that you actually have generated a lot of photons inside this box. And so when you open it up, you get a bunch of photons popping out. And so that's kind of roughly the idea of the Casimir force is if you have some sort of oscillating boundary, you can promote those quantum fluctuations into actual photons. And so in this way, again, it's something where you can think about you're generating photons from the quantum fluctuations, but it's not really that you're getting it for nothing, right? Because you're putting energy in to oscillate this plate, which is then producing the photons for you. And so if you have an oscillating mirror, you can roughly determine the amount of photons you can generate based on the first term is basically the oscillation frequency, how long you are oscillating it, and then this beta is a ratio of the speed of the plate to this speed of light. And so you can get an idea for how that would work. So this is the theory. And this has also been experimentally demonstrated in a few papers in the last decade. And so here's an example where they're using a superconducting quantum interference device, so a SQUID, where rather than actually shaking a macroscopic mirror, they were basically just changing the boundary condition electrically on this system. Similarly, people have done this with a fiber, where they've taken a fiber and you can send through a pulse, so you can basically just have dispersion give rise to local changes of the optical properties here again. So it's kind of like a mirror that would be moving, and you can generate photons in that way as well. So it has also been confirmed. So what were we thinking about? So the idea that we were interested in was, could we take some sort of material that is optically anisotropic? So this could be a birefringent crystal, it could be a grating, it could even be just a single rod, but something that is optically anisotropic, so through geometry or through the material properties. And then we want to rotate that object. And so you now have a spinning boundary condition with the idea being that this changing boundary condition, you have an acceleration, it's a spinning, that would give rise to the generation of photons, which you could then use for propulsion. And so that's why we've deemed that a Casimir torque thruster. And so when we started off, we did kind of a quick back of the envelope calculation to see if this kind of makes sense. And so if you want to know about the number of photons that you could get from a mirror oscillating, that's given by this expression here, which we had previously. And then we can assume that the oscillation frequency omega is the same as it's oscillating at what would in our case be a rotational speed. And so we have the velocity of the disk given here. And then that gives us the generation rate here, where it's based on what the radius is, the frequency of oscillation as well. And so if we pick a radius of a disk, we can get an angular acceleration, which then allows us to calculate the number of photons we could generate. So in this kind of very simple method, we can see that we can get about 4,000 photons over about 24 hours. That's what we get. And so the question we really had coming in is, is this realistic, and can we actually, perform a more accurate calculation and determine, is this something that would be feasible to do? And so that's where we started off with this seedling project. And so we started off trying to figure out, what is the best way to go about calculating this. And so we found some work from Cardar's group at MIT, where they were looking at using basically a scattering approach to the dynamic Casimir effect, which is quite attractive for the problem that we're trying to use. And so this is kind of where we have been focusing. And so no one's calculated a generation rate for a realistic system, but this at least gives us kind of a framework that we can further develop for that concept. And so the difficulty comes in determining the scattering matrix for the objects in question. And what I mean by that is the scattering matrix is relatively easy to calculate for a simple object like a sphere or something like that. But if you get something that is optically anisotropic and rotating, and you have to go back and forth between different reference frames, it gets a little bit more complicated. And so we've looked into two approaches here. So the first one is using a dipole approximation. So basically we can make an approximation based on the object being able to be treated just like a dipole, like an ideal dipole, rather than having some physical geometry to it. And then also a numerical scattering matrix approach, which would be the more exact, but also it'd be only numerical and not analytic in the final result. And so first, for the dipole approximation, we wanted to see what sort of geometries would be valid for this sort of dipole approximation. And so if we look at here, we have a cylinder. I'm thinking of a cylinder that we could then rotate and see what the generation rate would be based on that. So it has some total length capital L here, and we're going to rotate it at some speed omega. And so we want the length to be small enough that we can accurately treat this as a dipole. And we want to be rotating it slowly enough that, one, that we don't violate, speed of light or something like that, but also that the material doesn't just start breaking apart. And so we consider the velocity of sound within the rod to be kind of our limit there as a first approximation. So this gives us a way to think about a limit on the length and the speed at which this sort of approximation would be valid. And so that's not to say that this is the geometry that we actually would prefer to use, but just within this approximation, we know where it's valid, and we can kind of push beyond that if we want, but just knowing the validity of the calculations is important. So you can just kind of quickly think of the speed at the end of this rod, given the angular or the frequency at which we're rotating and the length of the rod. To avoid breaking, we're going to keep the speeds relatively slow. And so that gives us a relation between the length or the half length, lowercase l here, and the velocity of sound and the angular rotation rate. So for a silica rod, basically what that means is that we would be able to consider rotations on the order of gigahertz for maybe 100 nanometer scale particles, so between 100 nanometers and maybe a micron. And so this is interesting because this is kind of an experimentally achievable regime. There's a group from Purdue that was levitating elliptical objects, or actually these are spherical objects, but they were rotating them at about this rate, and particles are about this size. So we're knowing that at least this is a regime in which we could probe this experimentally if this looks interesting. So that's the first approach, basically using a dipole approximation in the scattering matrix method. The other one is doing numerically the scattering matrix approximations. And so here is a relatively simple form that we end up getting for the power that would be generated. So this would be the power from the photons being emitted, where it all really comes down to, we've got some constants and things like that, but it's just the scattering matrix here that we need for whatever the object is that we are that we're using. And so how do we calculate the scattering matrix? There are a few analytical expressions, but there really aren't too many of them. And most of the time, the geometry is not really what we're looking for. So for example, the closest thing that we found is this isotropic cylinder. But rather than rotating it kind of the way that we would like to rotate it, as shown in the previous screen, this is actually just rotating on its major axis. And so you can imagine if you're rotating like that, you're not actually going to be able to generate very much rotation, because the boundary conditions are not changing very much at all. And you can actually run through a calculation here, and it does in fact turn out to be quite small. So this is really not the geometry that we want. So what we do want would be something more like this, where we can either look at a single rod or an array of rods, which is depicted here. And so the way that we're now going about calculating this is using finite difference time domain simulations in order to calculate the scattering matrix. And so the way that you do this is we can basically set up, we have a numerical grid that's going to go through and solve Maxwell's equations. And we put our geometries in here that we want, and we basically are going to illuminate this system from different angles with different polarizations, and measure what the scattering is that comes out of that. So here's kind of the scattering matrix that you see with your inputs and outputs here, the A's and the B's. You can write it down here in matrix form. This is the way in which we are now approaching this calculation. And so the other thing that's nice about this numerical
3 minutes, Jeremy. Sorry.
3 minutes. Perfect. Thank you. And the other thing that's nice about doing it numerically is that once all of the mechanisms are set up for doing these calculations, we can then switch to different geometries or different types of anisotropic materials. And so with that, I'll just wrap up and say, kind of in summary, we have these two different approaches. There's an analytical dipole approximation approach. We have a numerical finite difference time domain approach, both using the S matrices. We need different matrices for each of the, for different wavelengths, different K vectors. It can be computationally rather intensive, but we have a computer cluster that we have access to that we can use for that. There's also a step that involves transforming these matrices back and forth between lab frames and the object frame, which is actually, it's a little bit tricky, but it's doable. And we have a collaborator who has a good bit of experience with the dynamic Casimir effect, and one of my postdocs as well that is helping out with these calculations. So with that, I will wrap up and say thank you for your attention, and thanks for putting on this workshop and giving us some funding for this. It's been a lot of fun working on this so far.
Thank you, Jeremy. Great stuff. Always enjoy getting a chance to hear updates on your work. And I think you told me at the beginning you are indeed down in Brazil working with your colleagues down there.
Yeah, that's right. Yeah.
Yeah, and that's in Rio de Janeiro, right?
Yeah, so that I'm not currently in Rio, but that's where my colleague is. Yes.
Okay, I'm just looking for an opportunity to pick on you. Sorry about that.
Yeah, no, no worries.
Just have fun with it. Okay,
Yep.
if you could stop sharing, that'd be great. Awesome, thank you, Jeremy. And just a reminder for everybody watching online, we'll do questions at the end of all these TED Talks that we have from everybody. So next up, we have a talk from Phil Lubin from UC, University of California, Santa Barbara. Phil is going to talk to us about the work that he's been doing on beam energy propulsion. The title of his talk is The Path Forward, Directed Energy Phased Array Technology. Phil, you have the con, sir, and I'll give you a 3-minute sweep when the time is. When the time's right.
Okay. Can you see my screen?
Yep, I gotcha.
Okay, you see full screen?
Yes.
Okay, very good. All right, so this is a progress report on where we are in our directed energy program. And we've been through some of this before, but this allows a really scalable concept to go from things that are quite small, actually, in the size of your hand, literally, up to things that are, you know, as big as you want. So someday we hope to build the Death Star, but that'll be in the future, so don't tell anybody. Okay. All right. So, you know, why do you want to do this? It's a very practical way to not only propel things for both direct photon momentum transfer, but also you can use it for propelling spacecraft in the solar system by converting the projected power on board to electricity and then using that to drive an ion engine. And these two different technologies are covered in a large series of papers. And now we have a 2-volume book, which is 700 plus pages. So just visit our website if you're interested. It is scalable. So this is a quite unique aspect of it. It's not as much like a conventional chemical rocket, which, you know, you can make little rockets, but they're not very useful for getting into space. But here you can go from very fast high mass solar system missions to lower mass relativistic flight missions for interstellar capability. So it really enables a whole range of possibilities which are currently not feasible. So I'll give you a quick overview. Deliverables, we're cutting metal and progress since the last report. So here's this is not all CGI. The stuff on this part is cutting metal. So we're building arrays. On the arrays showed over here, these are drawings, but this is real. Each of the sub-elements is about the length of your arm and about the diameter of your fist, forms a complete element. So all the photonics, that which produces light, a laser amplifier, if you will, and all the electronics, it's completely self-contained. You put in DC power and a fiber, and you just add as many as you want. And to make a larger system that's more capable, you simply add more elements. So on the left here, I show the size of a human. This is, again, is about the size of the arm in length. The diameter is set, by the way, because we want to start within the Earth's atmosphere for testing. Once you go into space, you can make the diameter larger. This has to do with the diameter required to deal with the first order perturbations, which is sometimes called the Fried length in the atmosphere, which for us is about 10 to 20 centimeters. So these are 10 centimeters. So we're working towards a 1 meter array, which is capable of powering things in low Earth orbit. And that's our goal for the system, is to build one of these 7-element subarrays, which can then be mosaicked into as large a system as you want. We've already shown that we could build and phase lock arrays up to 50 kilometers in diameter, which is more than we need to go interstellar. But we're curious, and it does work. And again, you can look at, we have now more than, I guess, 2,000 pages of papers and books. So the system topology is a nested tree topology. Each sub-element is shown here, which is one of these, and you add as many as you want, and we nest a tree in order to phase lock the system to the target, including perturbations in between, which in our case, the dominant one is the Earth's atmosphere. This is much better done in space. So in the future, you don't want to do this on the Earth. The far side of the moon would be a good place to do it. Front side is fine too, but some people might worry about what you could do with it that might be nefarious. So this part works. We've shown that the phasing topology works. We've done that years ago and shown lots of data on that. We get very good phase convergence, better than 1,000th of a wave over multiple kilometers of diameter of the array. And so that part works brilliantly. We've introduced atmospheric perturbations into our system and shown we can take them out. We'd still rather be in space. So on the spacecraft or whatever you're sending to, there is a beacon, which is a phasing beacon, which is basically a long coherence length laser. And we use that to lock to. So it's a very fancy adaptive optics program. This is a 10-meter example, which is something which I think could be built within the next decade. And a 10-meter example would allow you to get out to kind of geosync and beyond, actually out to about the moon. If you wanted significant amounts of power, you could send spacecraft through the solar system with something of this size. So anyway, it's a very scalable technology. All right, so there's a lot of things going on here. I'm not going to dwell on all of them, but just give you a quick overview. The whole system focuses around directed energy phased array. We'll show you a lunar beacon we're working on for a program on the moon. We're working on diffractive optics to lower the cost of some of the elements, and lots of algorithmic and photonics work going on. So this is kind of just an outline of where we are with this program. Where we're working here at meter class phased array. We've already built a lunar beacon prototype that works very well, long coherence length out to 30 to 50 watts. So it's good enough to put it on the moon if you want. And then the scaling and nesting, which I'll cover, we're doing 1 million elements simulated testing with a spatial light modulator, and that's working. And then we're doing some other things which are a bit optional. We built a phase stabilized fiber link, which may be useful. It's not really necessary, but could be useful for some things. And then we're trying to lower the cost of building the system, because economics is a huge issue here. What we built today would be prohibitively expensive to scale out to kilometer scales. So we need to get to much cheaper way of doing things, which if you look in our papers has always been to go to sort of photonic integrated circuit technology and other types of similar to what we're doing now, but make it cheaper. Okay, so I'll talk about each of these very quickly just to give you a fast update of where we are. But again, we are building arrays. Okay, so summary of progress, we have updated designs for everything. We even have to deal with things like thermal management. So those are fabricated and work. More testing in progress, but it does work. We have a phase recovery system that we've long had, and that part works quite well. We procured, as part of this program, another very narrow line width seed laser. So technically, each of these sub-elements is not a laser, but a laser amplifier. And then we have lots of students. So one of the things in our group is we typically have over a dozen students working on this effort at any given time. And one of our students presented a nice paper, which I'll show you in the next slide, on work in our laboratory that she's done as part of her senior thesis. Anyway, just an example, we have, I think, 70 papers now published, which you can go and check out our website. So this is just an example of what she was working on, which is the phase recovery and the photonics portion of the system. Okay, so this is what it looks like in drawing. Each of these is a complete sub-element, including all of the thermal control system, the photonics, the electronics, and again, DC in, fiber in, and build as many as you want of these and have an increasingly capable system. We're building 7 at the moment, but you could, if you had enough money, you could build an indefinite number of these. So there's all kinds of things with, you know, the technical aspects of how do you make the system kind of, you know, how do you make an iPhone-ish system? So it's got electronics on board on one side, all the photonics are on the other side. We do basically all of our photonics in-house, with the exception of the fiber draw for the fibers and the pump diodes. Although we can do the pump diodes in-house too, but it's cheaper right now not to do that. And then we have a fancy thermal management system and then a beam steering system at the end. So this is all built, this is all real. It's not just drawings. Okay, so here's an example of a system that we're building right now, which uses a slightly different final optic. Each of these optics is about 10 centimeters in diameter. We're working on plastic film optics to make them really cheap, and working on a prime focus design, which has a slightly longer length. So these are all details which you probably don't care about, but for us, it's a path forward to low cost designs. Just unfortunately, we have to do a lot of metal, okay, and semiconductors. So here's an example of one on the bench. This is a photonics amplifier. These are fiber-based amplifiers, although in the future we would go to other kinds of technologies, which we've been working with our ECE group for about 7 years now. But currently this is works very well. So we're staying with that for testing. And then we do all of our own electronics. We design and build basically everything in-house. And then lots of optical tables if you come to our lab. So here's just an example of how we test things. This is a seed laser. And the coherence of our system is set largely by the seed laser coherence length. So just to remind you, a kilohertz of coherence length of coherence bandwidth is equal to about 300 kilometer array diameter, which was enormous. And we don't need that, but we will show you that we can do that. Just one of my students reminded me the Death Star is 900 kilometers. So we're getting close to that if we want to, but can't afford to. Okay, we've already shown previously in our papers that we can phase lock to better than 1/100th of wave out to 50 kilometer diameter. And for reference, you may recall that between 1 and 10 kilometers is what we need for a typical interstellar class mission. Interplanetary missions are of order 50 meters, not 50 kilometers. So things are working very well. Our goal is to get greater than 10 kilometer coherence length, and we've long ago achieved that. So anyway, we measure the coherence length by basically offsetting the wavelength using a acoustic optical modulator, and we can frequency shift in that way. So I won't bore you with the details, but the result is we get a measurement of about 2.5 kilohertz approximately, 2.5 to 5 kilohertz. So that's vastly better than we need, and again, works great. This is a part of the program which I think you should pay most attention to, is that we're working on a 1,000,000 element phasing. So for us to build 1,000,000 of the elements that I just showed you would be prohibitively expensive. So what we're doing is using a proxy by using a spatial light modulator. So the topology is we have a spatial light modulator, which is basically something like a mirror steering element, except it's actually not. It's a spatial modulator, but each pixel modulates phase. And there's millions of elements on this device. So we can mock up as if we had a 1,000,000 element array and prove that the phase locking works. And so I'll show you some results from that. I won't bore you with the things that we were a little disappointed with. We're going a bit slower than we want. That doesn't affect this is a topology test, not a system test. Our system closes the loop in of order of microsecond. This is a topology test. So here's 512 element 1D array. You can see things are converging. We converge typically on order microseconds. And in the full array, we're already close to photon limited. Here's 1,000 elements. This is as though you built a 1,000 element array in 1D. So this is like you had a line of arrays, and it converges. An epoch is roughly between 1 and 10 microseconds. So we converge extremely rapidly. The reason this is important is, again, on the Earth, you have to deal with the Earth's atmosphere. So we want to converge in less than a millisecond. We're converging much more rapidly than that, even with 1,000 elements. And these are nested tree. So just here's a 2D array, 64 elements, 256 elements. This is the convergence pattern. And then here's 1024 elements. So we've shown that we can converge through this nested tree extremely quickly, even at 1,000 elements, and we'll move towards 1,000,000 elements. Okay. Now this one, by the way, starts in random phases, and we still converge very quickly. Excuse me. Okay, diffractive optics. We're working on very low cost replicated optics. Basically make a master, and it's like making DVDs. You just fabricate them by pressing, although it's a little bit different than that in our case. We're doing a roll-to-roll process. We start with a silicon diffractive optical element master, and then we go from there. So this is part of a program to lower the cost. You're familiar with Fresnel lenses to some extent by looking at lighthouse lenses, which is a poor example of that. Maybe little magnifiers you've seen that are thin. This technology works very well. We've already made some at the sort of about the 5 centimeter level. We want to go to 10. It's working. We were tweaking it up a bit to get the strain ratio higher, but it looks like it will work. Okay, just some, probably want to see this, but we can measure things down to the sub-micron level in making these things. They're about 30 microns thick, just for handling purposes. Okay, so I won't bore you with that. The lunar beacon, we would like to put a beacon on the moon. Idea is build a high power beacon. We've tested up to actually 30 watts now. That works fine. We even had a high school student who still has both eyes operational, by the way. And that works. Here's the breadboard. So this is not the one you put on the moon, but this is the breadboard. Again, we do all of our own photonics, so that's why it looks a little bit like spaghetti. And the spaghetti here are fibers. The core is about 10 microns in diameter, so electronics, etc. Okay, so it works well. We wouldn't put this one that we built on the moon, but we would make it quite small, about the size of your hand. And then we've been talking to companies about could we land it on the moon, etc. Okay, so it works, and the coherence length is great. We've already extended beyond 20, so this is a little bit out of date. So we want to package it into something that could be put on a spacecraft. So next steps. So we're going to complete the assembly of what we would call a subarray, which is an array of the hand-sized elements that I showed you, the ones that are about as long as your arm, and then test the efficacy of the global convergence, which we've done on the optical table, but now we want to build the full array so we can take it outside and, in theory, shine it up into space. Although to do so, we have to work with the DoD on laser clearinghouse issues. We are working on a new optical system, which is a little bit easier for us to deal with. It's a prime focus rather than a current system, which has multiple lenses. This will have a single primary lens, so that will make it simpler and give us a little bit better performance on our fiber tip actuation. A lot of the work goes into algorithms, as I showed you in the sort of million element proxy system, that becomes critical. So when you look at systems like this, you have to ask yourself, how are they converging their phase on the target? So if you look at things like a tactical weapons system, the general phasing is done at the aperture plane, not on the target, because they're not interested currently in shooting down things that are coming in from outside the solar system.
3 minutes.
Yeah,
Sorry.
I'm good. I'm almost done. So this is critical, is to make sure that you can phase on the target, because that ultimately is what you're trying to push or power. And as I mentioned, we are well into that. We've already shown we can, on the benchtop, phase within 10 microseconds or so, and the nested phasing that I showed you on 2 layers with the spatial light modulator, we're already at 1,000 elements, and we can push that to an order of 1 million. And then the lunar beacon, as I mentioned, we'd like to together. So I'll end 2 minutes early, and we'll take the questions, I guess, at the end. Let me see. Since I still have 2 minutes here.
Go ahead.
Okay. A lot of our some of our issues are related to thermal control. So here's just some pictures of how we do thermal management. It all works fine. The heat pipes actually were an interesting part of our program. We did institute that, and that works great. I don't think there's anything. Well, if you want to see what an optical bench looks like, you'd be terrified. You come in, and this is we have multiple tables like this, but they're just kind of wires all over the place. What they end up with is what I showed you, is that it's a highly integrated system that is a reproducible system. If we had enough money, we could make enough elements to build, say, a 3-meter array would be more than sufficient to power a spacecraft in low Earth orbit and to get to, say, the ISS or even beyond. And by the time you get to 10 meters, which would be of order 5,000 elements, I'm watching the time, Sunny. You can already start sending spacecraft in the solar system through power conversion on board the spacecraft. So we have papers on rapid missions to Mars, for example, that you might want to look at, including sending humans to Mars in 30 days. Even sending CubeSats with relatively low cost arrays. So this is all, it's very practical. The interstellar part, is a economics issue largely from our point of view. It's no longer quite the technology issue that it was in the beginning because we've beaten down many of the tall poles, but it does become an economics problem. So that luckily gets better because this is a exponential technology. So I will end 5 seconds early. Thank you.
That's great stuff. Awesome, Phil. Thank you for your presentation. As always, enjoy getting a chance to hear about what you guys are up to. That's good work good work and kudos to you and the team.
Thank you.
Pressing on ahead, we've got Adam Kay from MIT and John Bush, and Adam will be talking to us about their work titled Dynamic Vacuum Models of the Electron. Adam, you have the con, and I'll give you a little 3-minute squeak when the time comes.
Great, thank you. So hopefully you guys can see my screen.
We got it in presentation mode.
Awesome. So I always love going after Phil. It's going to be a big jump from the essence of practical to the essence of theoretical. So here we go. Yes, so I'm working as a postdoc in the Department of Mathematics at MIT in John Bush's lab. And with the gracious support of LSI, we are pursuing a project involving the nature of the electron and the possible dynamic theories of electrodynamics. So the unapologetically bold goal of LSI is to work towards unknown physics and unknown engineering. And it's pretty clear that in order to do this, we need to make breakthroughs in fundamental physics. In order to do that, obviously, you need to take a strong point of view on the future of science. So here's 3 quotes that I think are nice to combine to form a point of view. So the first is by Sabine Hassenfelder. In the past decades, physicists have not succeeded in solving any of the open problems in the foundations of their field. The wrong turn we made early on that led into the seeming dead end is resolving the shortcomings of quantum mechanics. And then by Duffy, the introduction of the ether as a main actor in physical processes will resolve a number of paradoxes in 20th century physics, which arose because of its dismissal. And finally, this beautiful one by George Polya, analogy has a share in all discoveries, but in some, it has the lion's share. So there is a research program that combines all 3 of these quotes. It provides analogies to quantum mechanics by assuming a background field. And I'm talking about hydrodynamic quantum analogs. So it emerged from the discovery by Yves Coudet and Emmanuel Faure that a particle of oil on an oil bath can vibrate indefinitely when the bath is vibrated, and it can even self-propel through a resonant interaction with its own wave field. So HQA is dedicated to exploring how this analogy applies, how the wave system and other related dynamical systems can exhibit behavior that's analogous to quantum mechanics. And there are an impressive number of analogs, some of which are listed here. And the thing that I think is maybe most interesting about this whole thing is that it's not even new. A very similar picture was proposed by de Broglie back in like 1925, 1927. And his basic physical idea, which he used to develop most of his entire research program, was that matter has some sort of oscillatory property. So he talked about the proper frequency of an electron and things like that. So in HQA, one of the limitations has been that everything is kind of restricted to 2 spatial dimensions. And the wave kernel there is a cylindrical Bessel function, and it creates a standing wave that decays with time. And John and I, working in collaboration with Matt Dury at the University of Glasgow, have kind of examined a 3D pilot wave system that uses a spherical vessel function. The basic idea is it sets up a vector field, which then winds up influencing the particle. So we discovered a helical spin state, which is unique to 3D, working in this direction. And we are currently wrapping up our work here. The plot to the left is the wave field of the helix, kind of cut through the center. So you're not seeing it go in and out of the page. And the plot on the right is the stability boundary for these helical spin states, which took quite a bit of work to get. The y-axis is gamma, which is the dimensionless wave memory, determines how long the waves persist after they've been laid down by the particle. And then kappa naught is the dimensionless particle inertia. So our analysis of the free particle is in 3D is pretty much complete now. And we're moving on to the next part of the research, which involves particle-particle interactions. And this leads us to Bjerknes forces. So this is a well-known force that exists in many areas of fluid dynamics. When you have a particle, like a bubble in ambient fluid that winds up getting irradiated by a sound field, the particles experience time average net directional motion, which results in drift. And it's said to be caused by acoustic radiation forces. So the sound field, which is it causes the bubbles themselves to oscillate. It irradiates the entire ambient fluid. That's called it's very analogous to the HQA, the vibration of the oil plate in HQA. And if you have just a single bubble in an ambient field fluid and you irradiate it, the bubble itself will experience forces, and those are called the primary Bjerknes forces. And then if you have two bubbles in a fluid that you irradiate, not only will the bubbles themselves kind of interact via the primary Bjerknes force, they also interact with each other. And that is called the secondary Bjerknes force. So these forces have applications in acoustic levitation, biomedical ultrasonics, liquid degassing, and even food processing. So the secondary force is usually expressed in terms of the existence. So I want us to kind of bookmark this idea. In the modern literature, this is largely the way that it goes. A is the amplitude of the driving vibration. Omega is the angular frequency. R10 and 20 are the equilibrium radii of the bubbles. L is the separation distance, and then omega 1 and 2 are the bubble resonant frequencies. And you can get both a attraction and repulsion depending on where the main omega, the driving frequency, lies between omega 1 and omega 2. So this is kind of the way that modern literature proceeds. As rich as it is, it almost never mentions the actual work done by Bjerknes, and there are actually two of them. It was a father and son. And what we today call the secondary forces were, in fact, their only concern. And they examined these forces in order to generate hydrodynamic analogs to electrodynamics. So the basic idea was that hydrodynamic flow lines have a very close analogy to the electromagnetic field lines. And if we imagine a steady outward flow generated, for example, by a source in the fluid, it has the same geometry and cross-section as the magnetic field at the pole of a long bar magnet. And then you can put them together and you get the exact same geometries. Two sources, as on the left, generate flow lines that are identical in geometry to two bar magnets of the same pole. And if you have a source and a sink, they generate the geometry of having two bar magnets with opposite poles. Finally, if you put a source and a sink right next to each other, they give us the bar magnet itself in cross-section. And Bjerknes didn't stop there. He kind of noted a wide variety of hydrodynamic analogs to electrodynamics, including the well-known one about vorticity, which was first demonstrated by Helmholtz. If you have two vortices in a fluid that are moving the same, well, it depends on their sense, but they will attract or repel each other based on that. And that has a direct analogy to the two wires with electric currents running through it in the same or opposite directions. And in fact, if you look at the flow lines and the magnetic field lines, they are basically the same. So this led Bjerknes to say that there's an extensive geometric analogy between hydrodynamic and electrostatic fields, which goes even into the most minute details. And then the problem that he had to solve was this idea that, well, you can't just have the source kind of doesn't really make that much sense in a hydrodynamic context. So how do we solve this? And the way that he did it was by considering periodic functions. So now you have a function that is just periodic, oscillating, and the simplest one that satisfies the conditions that he gave is this very, very simple scaled trigonometric function. And so now what you have is, you can imagine on the left, I don't have an animation for this, but it's like the flow lines have velocity directed outwards, and then it stops and it reverses, and it directs inwards, and then it directs outwards again. And you think, okay, well, how would this be generated physically? Well, you're led to the idea of a pulsating particle. And this is right away very reminiscent of HQA and the de Broglie clock hypothesis. So that's cool. But the really cool thing is that this idea actually gives us dynamics for free. So this is what I'm now going to show. So Bjerknes talked about this thing called the principle of kinetic buoyancy, which is, I don't think, really an accepted term in fluid dynamics today, but this is an explanation of the principle. And essentially what you do is you look at the acceleration of the fluid and you multiply that by the mass of the water that's displaced by the body. And it's similar to Archimedes' principle. And we can translate this into a kind of frame that's easier for us to digest. So the top line is the principle of kinetic buoyancy, and the bold U is just the velocity field. And rho is the density of the fluid, and then V is the volume of the object. So rho V is the weight of water that's displaced. So we have this fluid identity for small values of U and P. And using this identity, we can directly translate this principle of kinetic buoyancy into just a pressure gradient force. That's what he's talking about. And it's a very intuitive force. It depends on the volume of the object and the pressure. So if you're holding, a toy tent in a strong wind, you can do that with one hand, but you can't hold a regular sized tent in the same wind, even with both hands. So this is just what that is. So now if we imagine we have a pulsating particle in an oscillatory field. So let's just consider it to be kind of like a one-dimensional oscillatory field that vibrates around a particular point. And that'll be the blue line here, is just the oscillation force. So the field itself. So the fluid particles are going back and forth. And at the same time, in phase with this, the volume of a putative particle is also oscillating. And if you multiply these together and get the pressure gradient force, you get a force that's asymmetric. It is larger in the positive direction than it is in the negative direction. And so you wind up getting a net change in position. And so it looks something like this. You have this thing, it's going back and forth, but it goes back more than it goes forth. And eventually, this results in drift, obviously. So this is the basic idea. You have dynamics, and that's pretty cool. So now let's return to the secondary Bjerknes force, which is the force with two bubbles on each other. And at the top, we have the line of the way that is usually written in the literature that I've seen. Below, we have an alternate version that does not depend on the fundamental driving frequency of the irradiation in the fluid. So the Bjerknes father and son, they didn't care about the irradiation of the fluid. The way that they did it was like my mechanical pumps and engines, and they made actual like rubber balls like pulsate in volume. So this bottom expression is also an expression for these for the force between a pair of bubbles. Phi is the phase between them, and then on the right is just kind of experimentally observed trajectories for a variety of bubbles, and you can see that the force varies as the inverse square of the distance between them. Now, what we're going to do is we're going to just do some basic definitions and rewrites. So R1 is just defined as the radius of the first particle or bubble, and delta 1 is just like a small quantity. Omega is the oscillation frequency of the particle itself. Phi again is the angle between these two. We're going to set this to 0. And then we're just going to write Q1. We're just going to define Q1 to be omega delta 1 R naught squared, or R1 squared, sorry. And the bar over, by the way, means the average radius of the bubble. So when we do this, the force, the Bjerknes force, secondary Bjerknes force, reduces to this form, right? So it's negative rho Q1, Q2 divided by 4 pi over R, divided by 4 pi R squared. All right, so now this is what Bjerknes did. He made a kind of thorough comparison between electrodynamics and hydrodynamics. And he has like a kind of unusual notation. It's 1900s that he's doing this, and he mentions Oliver Heaviside all the time. So there's some translations that needs to happen, but what he spoke of as inductivity, we today call the permittivity. He wrote the permittivity of free space, the vacuum permittivity. He wrote that alpha naught. So we just translate that to epsilon naught, but remember that he wrote it alpha naught. And then in the hydrodynamic analog to that was something he called the mobility, or the specific volume, and he just wrote that alpha also. And all that is the inverse density. So if you recall, the equation we had in the last slide had rho on the top. And actually, if you compare that to, if you just express that in terms of the hydrodynamic mobility that he defined, you get the Bjerknes force. And if you compare this to the well-known Coulomb force, I mean, they're basically mathematically identical, except for this one change in sign. Now, this change in sign is not a mistake. It is everywhere throughout the entire analogy. So Bjerknes called it the inverse pole law. And he was able to develop this analogy to a very high degree of completion, right? He started with Maxwell's equations on the one hand, and he started with the Euler equations of perfect fluid on the other hand. And in many cases, he came up with a complete equivalence between the mathematical equations, with the one sole exception that the signs were always reversed. So this is pretty curious. And I think that it's a pretty big clue that when you have so much regularity of structure, but also a regular difference, there's something very interesting going on. So this is kind of where we are with the Bjerknes forces right now. And it leads me to the end of my talk, where I can explain kind of what we are currently investigating. So first of all, the inverse pole law.
3 minutes, Adam.
Great, I'm almost done. The inverse pole law seems like a fundamental clue, like I said. There's another difficulty with the analogy, which Bjerknes was very aware of, and that was that he could not extend to any dynamic properties of electromagnetism, right? So you don't get any propagation of light, you don't get induction. It's only static fields. The other thing that is, there's the connection between electricity and magnetism in the hydrodynamic analogy is not really particularly illuminating or really organic. you can kind of pick which one you want to be the good analogy, and then the other one. So what Bjerknes did generally is he had an analogy between the electric field and the hydrodynamic velocity. But you could pick the magnetic field and the hydrodynamic velocity, and then you're kind of left with the same situation of dealing with the electric field as before. Another difficulty is that the fluid vortices that Helmholtz explored, they have a constant intensity. So you can't really have vortices that oscillate. And that is a very significant breakdown of the fundamental approach of using periodic functions. And then finally, the flow lines that are generated by the pulsating particle don't really depend on space. They only depend on time in this treatment. And that is very different than the wave kernel that we are currently exploring in the HQA work, which is a spherical Bessel function. So that alternates, that depends on both space and time. So there's a lot of questions. I think that the analogy is extremely interesting. And I will leave the last word to Bjerknes himself, who said, "It will be clear after these few remarks that the problem of fields of force is of vast extent. We are only at the beginning of it." Thank you all for your attention.
Hey, thank you, Adam. I really appreciate it. As always, I feel like I'm getting a small peek underneath the sheet of reality, how it all works, right? We're kind of seeing how the gears may all fit together. So thank you for your continued Scooby-Doo investigation of the fundamentals of physics. That's good stuff, man. So appreciate it. All right, next up, we have Jerry Carson at University of Maryland talking to us about a fusion concept that he's been working on. The title of the project that he's working on is Direct Fusion Drive based on centrifugal mirror confinement. Jerry, you have the con. If you would share the presentation from your desktop, that would be great. Sure. And I'll give you a 3-minute squeak.
All right, can y'all see the presentation?
Yes.
Okay, is it in full screen mode yet?
I'm still seeing your PowerPoint.
Okay.
You might have shared the wrong screen.
All right, here we go. So do you see now? Okay.
Yeah.
So afternoon, everybody. Thanks, Sonny, for the opportunity to share where we are on this particular project. Ray Sedgwick, unfortunately, was not able to make it today, but he sends his greetings. Just like to mention, I am part of a team at the Space Propulsion, Power Propulsion Laboratory at Maryland. We have other folks who are working more heavily on the power conversion part. I'm working on the propulsion piece that in some ways incorporates several pieces of other researchers' efforts. In that sense, I have a bit of a systems engineer role, but as you'll see in this presentation, we do some deep dives into the necessary plasma physics to where we want to go. We'll start off with just a review of what centrifugal confinement is and how it works, and then a run through our current status in terms of modeling and what kind of performance we think we could get out of this system, and then what the operation of a direct fusion drive might look like, and what that potential is. Our objective is to get a technology readiness level of 3 for this, and one important part of that is the hardware and the experimental end of it. And I'll talk a bit about what's going on with the development of a prototype of a terrestrial reactor that's using centrifugal confinement that has been built by our physics department in collaboration with the University of Maryland, Baltimore County. So centrifugal mirrors, it's the idea of taking a high electric field in combination with a magnetic field, and that equation in the middle of the page is a vector equation that shows you the drift velocity that comes with combining those two. Drift is kind of a misnomer. This can be millions of meters per second, and because of that, it allows you, it results in both axial and radial confinement. The graphic to the bottom left is a simulation in 2D of a centrifugal mirror confinement and showing the contours of Mach number. You know, that blob off to the lower left is the concentration of confined plasma. Schematically, it's shown on the right-hand side where you can see the electric field that is crossed with the magnetic field, and that confines the plasma well, that red region of burning plasma or confined plasma in that little section of magnetic field there. So that's basically how magnetic centrifugal mirror confinement works. This is the CMFX machine that has been built and is currently in test at University of Maryland. They have been running for a few months now, so far only on hydrogen, primarily to check out the system and help them get their instruments calibrated. They just got their dewar of deuterium that anticipate using next year for where they'll actually be achieving fusion conditions. But there's a history to this type of confinement. In the US, there was the Ixion machine in the 50s and 60s. Sweden, there was 20 years of work on their F1 and F3 machines. And one of their researchers, Mr. Leonard, is the one who first proposed the idea of using centrifugal confinement for fusion. And in the Soviet Union, they built a large machine, the PSP-2, instead of using a central electrode and a B field. They used ring electrodes to generate the electric field. Sort of an interesting take. The Maryland confinement experiment extended this idea. That was also done at University of Maryland in the early 2000s. And they demonstrated centrifugal confinement of a 100 EV plasma, which was pretty cool at the time. So they've got their sights set on higher things right now, which includes achieving fusion conditions. Their instrumentation and diagnostics are going to include Thomson scattering, as well as a neutron detector, which will be sort of the indication that they have in fact achieved fusion. And that's in their campaign plan for next year. So we're going to use this idea in tandem with a propulsion system. And the idea is to have a CM fusion reactor in tandem with a warm plasma. And the warm plasma has a couple of functions. But because it is a mirror device, there are particles that leave through the front end and the back end. And that's by design. We like that. In fact, we want more out of the mirror ends than the terrestrial people do, because that's our propulsion. But we use the particles escaping the jet side for propulsion, but we also recover particles coming to the forward side to generate power to run the reactor. And that's a requirement for this system, that the reactor is self-powering. Having the particles leave through the mirror, the jet side mirror, they enter a warm plasma, they heat it up, and that heated warm plasma leaves through a magnetic nozzle and generates thrust. A couple of the things that the warm plasma does is it allows us to trade energy for thrust. A pure fusion engine would have very high specific impulses, very low thrust. In this type of concept, we expect that the fusion products will heat the plasma. We can get higher thrust at lower specific impulses, obviously, but it also mitigates what's called the frozen end condition. That is the tendency for collisionless plasmas, which a fusion plasma essentially is to remain attached to magnetic field lines. And there are several measures for what that is. We use, or we were calculating the Cowling number, which is an indication of ion detachment. And I'll have a chart or two on that in a few charts of what we want to achieve there. Basically, a Cowling number of 1 is indicative of a detached plasma, one that can generate thrust. And as I mentioned, the energy leaving from the upstream mirror is converted into power. This chart is a schematic of the system, and the two red regions there are the annulus of the reactor plasma, and you can see the electric field in blue, and the green dots are the representation of the magnetic field. The fusion products follow the magnetic field lines into the warm plasma, the alphas and the thermals. And then there is a introduction of a propellant, a beta species, and that mixture is heated, and then it expands to the plasma, the nozzle to generate thrust. Again, on the upstream side, we are sending alphas to a standing wave direct energy conversion system. That's our baseline. There are other systems or concepts for power conversion that are being considered and studied at Maryland, but that's our baseline for the system we're projecting right now. So there's several models that have been developed for this, four in particular in my area of research. The first one is a 0D reactor model. This performs a Lawson criteria calculation, which is where we look at all the potential losses in a plasma, the radiation, the losses that go to heating the fuel and then ionizing it. And we have to cover those, but we also have to cover the power that goes into the reactor. That's the IV0 over VR. And then the first term in that equation is the fusion power. That G is how much power goes out the forward and aft mirrors. So anything that's left is used to keep the plasma burning. The G factor, though, if you multiply that by the fusion power, is what we use that circles back into the IV0 over VR, and it ends up being in the jet side power as well. So that model is in place. It's well characterized at this point. We've benchmarked it against the physics department's model, which they are using for experiment design, and it's we verified that the results are accurate and comparable, if not very similar. The next model was a 0D warm plasma model. We wanted to have something to give us a rough idea of what the propulsion efficiency would be, but was relatively simple, and that's essentially a first law balance of the power coming in from the reactor and losses related to heating and ionization, and then what might be left over for jet power. The 1D plasma model is what our major effort is right now. It's that equation there is that you see is now the vectors are for they're different species in the continuity equation. We solve also the momentum equation, and then the temperatures of the ions and the electrons for the energy equation. The F quantities are fluxes, and the S quantities are source terms. So this equation was recast as a finite volume tool, and it is we are running cases right now on our high performance computing cluster at Maryland, and right now we've got about 27 cases on the run matrix. We've successfully completed 9 of them, and we got 3 in run right now. So we're making progress. I expect to be done with the first cache of runs, sometime by middle of September. The final model is a propulsion model. It's a polytropic expansion based on nozzle conditions that we get from the reactor model and from the warm plasma model. So all these models are federated, and the output is the thrust and the specific impulse and the efficiency of the overall system. What you're seeing right now is just some output from the 0D propulsion model, showing the specific impulse as a function of the bypass ratio. The bypass ratio, or chi beta, is the ratio of propellant flow to the prompt fusion products leaving the reactor. That's normally on the order of 10 to the 3 or 10 to the 4, depending on the specific impulse you want. So you can see the higher the chi beta, the lower the specific impulse, but the higher the thrust. So that's what you would expect. And you can see here that just from a simple model that specific impulses in the tens of thousands of seconds are possible, while still delivering thrusts in the orders of 2 to 10 newtons. So this is a fairly attractive situation where you can get hundreds of kilowatts of jet power, even up to a megawatt of jet power from a relatively compact system. I've just moved to chart 10, which shows some initial results from our 1D plasma model. What this is, it's a transient model, but the idea is to use that transient model to get to a steady state condition that we can then use to predict the performance of this system. And the first one is the evolution over one confinement time of electron temperature. And you can see in that red line is the warm plasma, 0D warm plasma prediction. So we're pretty good shape there. The chart on the right is the power stack up. The line, the top line is the power is actually deposited, and then you see the jet power in purple and the heating in gold, and the ionization in the bottom light. That little notch on the bottom turned out to be a bug in the code that I was able to fix over the weekend. So even in production, we're finding things and wringing them out and making the thing run faster. So these are this is sort of our benchmark or our flagship. We want to have a 200 kW jet power delivered sort of configuration. This is what our primarily interest is. We think this is a good size for a practical system. The chart on the left is the plasma velocity over the nozzle length in the from 0 to 5 meters. The electron temperature is showing to drop. Because this is an annulus, this isn't on the center line. This is on the basically about halfway through the chord of halfway through the radius, which is the maximum density and energy of the plasma. And the chart on the far right is the Cowling number, which is an indication of ion attachment. And we achieve a Cowling number of unity about halfway through the expansion, which means the ions can detach and we can generate thrust. And this is results in about Mach 6.5 at the nozzle exit plane. We getting 2 newtons of thrust and 18,000 seconds of specific impulse. So this looks like a fairly good place to concentrate on for practical systems. And moving into the idea of practical systems, the way you would operate these things is very different from thermonuclear or even conventional chemical systems, where you have a very short, high power burn. And then when you get to your destination, you have the burn to get yourself into arrival orbit. These systems will be operated pretty much continuously, and at mid-mission or shortly thereafter, you just reverse the direction of thrust to start slowing down. But the key is that these high jet powers, hundreds to thousands of kilowatts of jet power, are really what we need to get to the outer solar system. So on that note, viable commerce and future space exploration, we want multiple megawatt power generation, high specific impulse, moderate thrust levels, and low system specific mass. So we're really looking for like 20 kilograms per kilowatt types of alphas for that. Unfortunately, I wish Jason had been able to stay on because this reference 4 is his paper where DFD could make a trip to Mars and very quickly compared to nuclear electric or thermal nuclear. And for Saturn, we could get there in less than 3 years. So that's pretty attractive performance. And just moving on to some other missions, the Uranus orbiter and probe is proposed for a flagship mission for NASA's recent decadal study. Would take 12 years to reach Uranus with a gravity assist from Jupiter. A DFD-CM powered mission could get to Neptune much faster and deliver 4 atmospheric probes. So that's a pretty attractive mission. And then looking to interstellar exploration, the interstellar probe currently under study by NASA would reach the heliosphere 1,000 AUs 50 years after executing an over-Earth maneuver. A second generation interstellar probe with a 250 kW plant could reach 1,000 AU in less time, assuming a moderately aggressive propulsion system specific mass. So that is a quick run through of what our vision is and where we are on our research. The next steps are to complete the analysis we're doing right now, so we sort of a cohesive and coherent set of analyses that we can move forward to in the next step, which we hope is be starting to get into the experimental world and join our brethren in the physics department starting to build prototypes. So that is my conversation for the afternoon, Sonny.
Thank you, Jerry. I appreciate that. I kind of sensed you were getting close to the end there, so I didn't give you the 3-minute squeak. So I figured you're gonna snap the chalk line at just the right spot. So
okay, so hope I didn't go over.
No, you're good. You're good. Thank you for your presentation. It's good to get updates on the progress. I'd like to see some of the applications as well. It's always good to see that. So thank you for that. So next up, we have our last talk of the afternoon session and the last talk of the day. We have Chathura Bendatunga joining us from Australian National University in Australia. Jerry, if you could stop sharing your PowerPoint. And Chathura will be talking to us today about his team's project titled Navigating the Atmosphere, Transferring Terrestrial Beamed Energy to Light Sail Spacecraft. So Chathura, if you're on, go ahead and share your screen and I'll give you a 3-minute squeak when the time comes.
Awesome. Thanks, Sonny. Can everyone hear me? Just checking.
Gotcha. 5x5, and we see your presentation
Awesome.
Presentation.
Well, thanks everyone, and good morning to you all from Canberra, Australia. Yeah, it's my pleasure this morning to talk to you and give you an update on what we've been working through with this LSI project. As was introduced, the goal of our project is really quite focused. We're looking at this particular problem of getting terrestrial beamed energy, as was discussed by Phil earlier in this seminar series, but getting that through the atmosphere in a coherent way and getting it directed at a light sail spacecraft. Before I continue too much further, I'd like to acknowledge the team. Paul and Mike, we've been working together for a while on breakthrough starshot and optical phased array related activities. But Noah is a undergrad bachelor thesis student who's came to me in his first year with aspirations of working on breakthrough starshot and exciting interstellar missions, and he held that dream, held that vision, came back to me 4 years later, having now gotten to the end of his bachelor's degree, and it's a great pleasure to be working with him on this project. So to dive in, if I may change, there we go. To dive in into what we're trying to achieve, it's really using light and the energy that it is able to carry as a means to power space travel quickly and to destinations that are either interplanetary within our solar system or interstellar. And a requirement of this, a requirement to be able to do this, is really to deliver a large amount of optical power. And for these interstellar missions, that level of optical power is on the order of gigawatts. So to do this, we not only need a high output power, but we also need a large synthetic aperture. This means a phased array, an optical phased array, that is made up of many elements. Order of 100 million is the target during the initial proposals for Breakthrough Starshot, for example. And as part of that, we need a phasing solution. This 100 million set of apertures that are all independent kilowatt class lasers all need an effective way of being coherent in amongst themselves, but then also being coherent once they propagate through the atmosphere. And as part of the initial Breakthrough Starshot work that was done at ANU, an architecture was proposed to achieve a solution to that problem of phasing the array, and that problem of maintaining that phase coherence while the array propagates through the atmosphere. And so what we're doing in this project is really setting up the real-time acquisition, phase correction, and feedback system for that atmospheric correction signal, for that atmospheric correction. And a schematic diagram of what we're trying to achieve here is shown here in the bottom right, which I'll zoom in and go through briefly. And this is what we discussed in the introductory talk. But the proposal is to have a beacon spacecraft, which is within the isoplanetic angle of the laser sail. Now, you might ask, why not just use the reflection from the laser sail as your reference? Why do you need a beacon spacecraft? Well, as this laser sail accelerates away, it's moving away from Earth. The round trip time of flight to that sail is now increasing. And so the information you're able to ascertain from the atmospheric measurement, that control loop starts to slow down and reaches a point where it's no longer viable to use that as a feedback signal. So having a beacon spacecraft dedicated to wavefront sensing is the way to go. And we've seen that in a number of proposals put forward for this type of work. So if we start at the beacon spacecraft, we have what we hope to be a relatively flat incoming beacon wavefront. Across the array, which we've shown here as segmented into these 8 steps, this wavefront will become distorted. And so what we do at the array is we measure the average phase across each of these apertures, such that we get this step profile of what the atmospheric disturbance was. And this allows us to correct for each aperture independently. And so with that pre-correction applied, what we'll see at the sail is a wavefront that is now reconverged back to a flat phase front. Now, there are conditions on this. One, you can see that we're averaging across these individual apertures. And that then imparts restrictions on the size of individual apertures that we use. That's also determined by the atmospheric seeing conditions at the launch, at the site in which one of these arrays might be built. But to delve more into the details, what this project is focusing on is really how do we do this step 3 of measuring those inter-emitter phases and measuring them with interferometric precision, and then also converting them into a feedback signal that's appropriate for use in the array. So if we zoom in now on that part 3, what does the array look like? And here I've just drawn a really simple cartoon of the functional aspects of this array for 2 emitters. Now, granted, there are many more, but we can see that if we can get this measurement between 2 emitters, we can do this for successive emitters and build up coherence that way. So this is really the fundamental building block of what we're trying to do. So here we've got on the right, we've got our beacon, and it's illuminating back towards the array. We have some amount of light being captured by each of the optical phased array emitters, and they travel back towards this first coupler. This first coupler we'll refer to as the arm coupler, and the second coupler we'll refer to as the detection coupler. Now, critically, the optical phased array output only goes through this arm coupler. And then all of the sensing, all of the interferometric measurement is made relative to a local oscillator field, which is injected at this detection coupler. Now, the thing that we're trying to measure here really is the inter-emitter phase difference. It's this delta L here. And I've drawn this delta L as an actual physical difference between the placement of these emitters, and that very well might be the case. Of course, it's going to be impossible to manufacture a optical phased array which is optically flat to within a wavelength, and so this delta L here, this physical delta L, is significant. But also, this system will capture any optical path length that is different between these two. So not just physical, but also any changes in refractive index, local changes in refractive index between these two paths. And so with that information of the inter-emitter phase difference, we can ascertain information of this inter-emitter positioning error, and also any of the phase shifts due to the atmosphere that are different between these two apertures. Now, the challenge here is that we have this OPA seed. This OPA seed is extremely high power. For an individual aperture, it's going to be on the order of a kilowatt. And so we need to be able to distinguish not only we need to be able to distinguish the beacon light field from many reflections from within the system. So here, this arm coupler is just splitting between two, but in fact, it will split between many apertures. And so we'll have many high power fields that have partial reflections within the system. And that will mean that we'll need to be able to distinguish a small beacon field from these relatively bright internal reflections. And then there's also scattering. Scattering is another issue from the atmosphere. In our case, we're not using it as our measurand, and so we'll need a way to distinguish from scattered light as well. And so the proposal for this really is to use a multi-wavelength approach. And we've also seen this from a number of proposals, which is to use a beacon at a different wavelength. The key thing, though, with what we're trying to achieve is that we're trying to achieve an interferometric measurement of the output. We're trying to achieve better than a cycle precision on the output field of that OPA, which now is at a different wavelength. And so we need to factor in the fact that we're measuring now our atmosphere with a different wavelength as well. Now, this in itself is not an issue if we have good knowledge of what our path length is. And when I say good knowledge, I mean to within a wavelength or a few wavelengths. And that's because the rate at which optical phase is accrued is dependent on the wavelength. And so if we have multiple wavelengths, we're accruing phase at different rates. We measure at one wavelength, that phase does not correspond to what we want to actuate back on the array. And so what our algorithm does is that we say, okay, let's instead have two beacon wavelengths, which gives us two slopes to work with. And from these two slopes, we can then get an absolute measurement of this delta L. or infer an absolute phase measurement at the emission wavelength. And it's this conversion from the measurement wavelength to the emission wavelength, which is what we're really trying to test out and make sure is working in real time. And so for the keen-eyed amongst you all, you'll recognize that this type of approach is very similar to two-color interferometry. And two-color interferometry, what we're effectively doing is we're taking short wavelengths, the precision of short wavelength measurement, for example, an optical measurement, and we're synthesizing a synthetic wavelength, which is proportional to the product of the two wavelengths divided by the difference. And so this extended wavelength now, this extended synthetic wavelength, is what we're measuring against. And by working with this, we're able to then extend out that ambiguity range, which would otherwise inhibit us. So moving into a more detailed schematic of what our architecture will look like. This is the functional topology that we operate with, and this has been demonstrated in prior art by us as well. But what we're adding here is now our two beacons, and we're adding a wavelength division multiplexing system at the end in order to separate out those two beacons from our internal control fields. As before, we have our arm coupler back here and our detection coupler here as well. You'll note that this arm coupler now has reflections from n different emitters. And so here you can kind of see the compounding nature of dealing with this backscattered light. Critically for us, we're measuring the beacon fields at this top level control systems. For our larger arrays, we'll have a nested control system, which will have many control layers. The atmospheric correction operates at the top level. And the critical thing that we've achieved with this architecture is that the optical elements in which govern the internal control are also the optical elements that govern the atmospheric sensing as well. And so we're actually measuring in the end the exact same optical paths that we need in order to stabilize the emitted field. To go through the mathematics of what this correction looks like, this is our phase shift between successive emitters, and this is at the emission wavelength. Let's say that we measure at beacon wavelength 1 and beacon wavelength 2. These are our input measurements. The beacon 1 measurement is used to estimate the phase difference at the emission wavelength. And then we use the ratio of the synthetic wavelengths between beacon 1, beacon 2, and the emission and beacon 1, as well as the beacon 2 phase measurement to synthesize the fractional correction due to the wavelength differences between the three fields present. Now, as part of this calculation, you also get this second term, and this second term is dependent on the integer number of wavelengths different between beacon 1 and beacon 2. And this is, you can imagine this as occurring when your measurement distance is large relative to the ratio of your synthetic wavelengths. Now, because we're after a phase correction and not an absolute path length necessarily, if this is modulo 1 cycle, the correction algorithm is transparent to this residual error and it doesn't become an issue for our measurement. And so by choosing synthetic wavelengths which satisfy this being an integer, we're able to extend out the physical range or physical path length differences that are tolerated by our measurement system. And just a reminder, the synthetic wavelength. So what we're trying to do is we're trying to make sure that this residual error is small. So what we're doing at the moment, we've done simulations, we've presented and published those simulations, but those were done all just conventional software simulations in MATLAB and other platforms. We're moving now to our real-time system, and for prototyping, we use National Instruments. It's a lot easier than having to do a full embedded system design, which takes a lot of time. So to start off with, we used some hardware we had in the lab. This is a National Instruments 5781. You can look up the part numbers. Critically, it has a 100 megasample per second input-output ADCs and DACs in a 2x2 configuration. And it's running a Vertex 5 FPGA on it. This is quite a few generations old compared to the current Xilinx lineup. So with the LSI support, we were able to upgrade to a newer system, which critically has more input and output channels, and that runs slightly faster as well. This
three minutes, Chitra.
Thank you. This is great as it gives us a lot more flexibility, and we're transitioning to this at the moment. And we're looking at putting in a number of improvements, namely reducing quantization noise and including a more sophisticated noise simulation. So as part of this hardware and loop simulation platform, what we're trying to do is we're trying to implement our real-time phase measurement, which we've done before, but also our wavelength projection algorithm, which I've just talked about now. What's using up a lot of the DSP resources are actually these wrapper modules, the proxy signal generation and the performance calculation. So to talk about the proxy signal generation, what we've got on the user side is we can input path lengths and the wavelengths of the three fields we're computing. We have a floating point system to convert those to phase measurements with floating point precision, which is then passed to a fixed point DDS system on the FPGA, which generates proxy photodetector signals, which are then bussed into our phase measurement system. Now, critically, this is able to run all at 125 megahertz. So we're able to effectively simulate the entire photodetector bandwidth with this system. The RF phase measurement we're opting for currently is an open loop readout. This is a standard quadrature demodulation. We're operating with a nominal readout bandwidth of approximately 50 kilohertz. We've gone for open loop at the moment because it allows us for fast implementation and ease of debugging, but we'll switch over to one of our phase lock loop architectures in due time, especially when we get optics on the table. And this will allow us to reduce the latency of the system even further, which is necessary for feedback. And then to the meat and potatoes, the parameter sweeps. This is all data that was measured in real time off the FPGA. The plot up the top, what we've got is in the gray, we have the emitter wavelength measurement, and then in the red, we have the corrected measurement, which was synthesized from the two beacon measurements. We can see that they overlap great for small wavelengths. This is lambda 0, 1 lambda, 2 lambda, just normalized to the wavelength. We can see it matches up. But then we can increase the path length difference between our emitters to 1 meter, which is many, many, many cycles. And then we can still see that we've retained good correlation between the two measurements, the truth and the synthesized correction. Looking at the error on its own, we do see that there is an error that occurs, and this error manifests really when we have less than ideal wavelength knowledge of our lasers. And this was a parameter that we initially knew was going to be critical for the system to operate. And we can see that with 100 kilohertz error, we're getting a few milliradians error in the phase. And then with a 1 megahertz error on the wavelength, we're getting approximately lambda on 150, which is again well within our tolerances. So the system now is working quite well. The top panel up there, this is kind of the interface that Noah has built. One of the things that we're doing at the moment is just characterizing the length to phase conversion on FPGA, so we can do that in real time and now inject noise as well in real time. We've been stamping out quantization issues, which if people have done anything with DDS generation before, know that that's always a bit of a pain, especially when simulating signals with fairly large dynamic ranges. And the new features that we hope to add by the end of the project include length and noise injection, length modulation, I should say, and similarly for wavelength modulation as well. So we can kind of dynamically change those. And in the fullness of time, we'll be able to get a system that's directly able to plug into our phased arrays, and we should be able to test it out in the field. Thanks very much for listening.
Chatura, thank you for the presentation. Thank you for giving us an update on all your amazing work. And most importantly, thank you for joining us at like 5 o'clock in the morning, your time, man. Woo! So that's dedication, my friend. We appreciate you.
We're awake.
So having worked for NASA for 20 years, definitely know the fun and challenge of balancing time zones, working with the time zones all over the planet. So thank you. So I guess now we can switch gears and go into some facilitated Q&A for all the projects that we just heard from, all 5 in this afternoon session, Houston afternoon. And then, of course, if there were questions for any during the first 4 that somebody didn't get a chance to ask and they thought of between now and then, we're happy to go back to that. So let me open up to the panel. What are some initial questions folks may have for one another? I will go ahead and take Chairman's prerogative then and ask some questions. Phil, on the work that you're doing with this beam energy propulsion, kind of in the maybe even in the same zip code as some of the stuff we saw from the work Chatura is doing. What would be, in your mind, a couple of good terrestrial applications for that? Right, we've got these space things. I got all that, but what would be maybe some terrestrial applications for that?
Yeah. First of all, Chatura, great talk. Really appreciate it. Very nice. So there are some that I could imagine, but honestly, I think one has to look at this very, very carefully for terrestrial applications. I mean, one could think about things like, last mile, literally terrestrial on the ground. I don't think that there are some applications of that is useful. I mean, we've done some DoD stuff where that becomes interesting. Other applications are really sort of airborne, so ground to air, air to air, drone applications. We have some things going on in that area. We're finishing up a multi-year project with NASA on some lunar applications, and I think a lot of the issues that we're seeing in kind of both of our talks will come down in the end to the application space and the economics of that application space. And that's something that would be nice to have a pretty thorough discussion on, like, where are we going in the long term here, and how do we get there, and who is going to fund it at the levels that are required. So in terms of terrestrial, yes, some point to point on the ground, but it's very limited, I would say, and mostly in our case, largely DoD related. Ground to air is very important, and air to air, we're working on that part.
Chatura, do you want to chime in on some comments?
I think that's right. The ground to air, I think, is a space that there is room to move. And what I like about some of the stuff that we're doing is that we've built in a cooperative nature to the architecture, which I will say does restrict some of the applications. But for me, it's in those communications, in the energy delivery, in those kind of spaces where I see the short term, let's say, within Earth's atmosphere benefit. Yeah. Thank you. But broadly agreeing with Phil's assessment. Yeah.
Awesome.
I have a question for Chatura, just a little thing. You were talking about the beacon spacecraft, and I'm wondering if this is attached to the solar sail. I think it must be. And is there any way of capturing some of the energy that is beamed in that direction and using that to kind of shoot a beam back through the atmosphere to Earth?
Great question. The beacon spacecraft is not attached. It just needs to be within the isoplanetic angle of the array, which gives it a patch of sky that it needs to remain in just for the duration of the launch window. So if the nominal launch window is order 10 minutes, and from that restriction, you can then design an orbit for a beacon spacecraft such that it remains in that patch of sky for the 10 minutes that it's required there. With regards to the second point of harnessing energy and beaming it back, that's something that I don't think we've considered yet. We've considered taking a direct reflection from the sail, for example, as the measure arm that we're looking at. But the issue there is that the round trip time to the sail is going to increase very rapidly as the sail accelerates away. And so that really becomes the restriction of using something on the sail itself as the measurement tool.
Got a couple questions from YouTube. The first one I think is for Jeremy. Is from Todd Desiato. How do you tell the difference between photons excited from vacuum fluctuations when you're accelerating it and the photons emitted by Larmor radiation due to accelerated ions?
Yeah, it's a good question. So the dependencies are a bit different. So the spectrum, for example, is different in this cases. And the other thing is that you really want to make sure that you do not have any sort of trapped charges. And so those are kind of the ways you would check this. So one, making sure that you have just neutral objects, and then the spectrum with which you get generated looks a little bit different too. And also the dependence with acceleration.
Thank you, Jeremy.
Yeah.
One more question from YouTube. And this is for you, Jerry. It's kind of a two-part. The first one, I think he's asking if your MATLAB simulation code was published. But let me give you the real question here. Regarding the fusion drive, is the drive designed to run continuously during the year-long deep space missions?
Yes, it is designed to run continuously. The limiting factor that we believe is the SWDC is supposedly 80% efficient. That's what we're shooting for. So for a continuously running system, we have to be able to radiate 20% of that energy back out into space. So that's sort of the limiting factor there. But the simulations that we've run indicate that the system can self-power, and that's the main thing in terms of a viable system.
Awesome. Thank you, Jerry. And I have a quick question for Adam. So Adam, when in all of this kind of sleuthing and digging into Bjerknes forces, coupled with everything you know to date in your and John's exploration of hydrodynamic quantum analogs, are you really excited about what you're seeing, the hint of what you're seeing in the Bjerknes forces, or do you see there's some serious breakdowns? This is like a colloquial question, right? I don't need the specifics. I'm just trying to, what's your feel on things?
It's both. I am very excited. I think that the fact that there are analogies to the main pillars of physics across the board, fluid analogies, is very revealing, right? There are analogies for quantum mechanics now. There are these analogies to electrodynamics. There are analogies to general relativity. So that is very exciting. However, things aren't fluid or oil or water. So you know that the analogies break down, you expect them to break down. And I think that where it becomes very helpful is when those breakdowns are very regular, right? So the inverse polar is an example of that, where that is like a difference that is repeated everywhere in the Bjerknes analogy. And like I said in my talk, it just seems like a massive clue. There are other breakdowns in analogies that don't seem to give you anything, and just kind of maybe make the analogy not so good. And that's another place that you have to look if you really believe the analogy is going someplace. So yeah, the answer is it's both.
Gotcha. Hey, John, do you want to add some comments to that? You're on mute. You're on mute.
Yeah, I was just going to mention, I prompted Adam to mention this, but we just discovered this analogy, which I hadn't been aware of, which was the gravito-electromagnetism, which is an analogs between GR in the weak curvature limit and electromagnetism. I really wasn't aware of this. And, with the bouncing drops, there are many well-established analogs with electromagnetic systems, including self-induction. And this allows an analogy between E&M and GR allows one to think in terms of gravitational self-induction, which is really quite remarkable. And, in terms of big picture, I think the notion that, we have these well-established hydrodynamic analogs with GR, which is sort of work pioneered. They got about a 20-year head start relative to HQA. So this is Unruh's work and those of others. That's relatively well developed. And now we have the hydrodynamic quantum analog. So to think that you could, hydrodynamics could provide the church at which to marry the two, quantum mechanics and GR, is rather a nice thought. So we're certainly pursuing that. And again, this latest analogy allows us to do the first single particle GR analogs, because the GR analogs usually involve waves interacting with hydraulic jumps or vortices, and we can now do a single particle analog. So it's pretty exciting.
It's great. I love that cup. That quote that's almost like coffee cup worthy, right? The church at which to marry the two. I like that. And then I also have to do a hat tip for Phil to try and work in a scale measurement referring to the diameter of the Death Star. So I was paying attention during your talk. I thought that was awesome. So what other kind of questions we got in the group?
Hey, hi. I had a question for Jeremy about your Casimir torque, and you said your back of the envelope that 40,000 photons would be generated. Did you figure out what sort of force that represented? Is there a way of doing that?
Yeah, I don't recall right now what that number comes out to. But yeah, I mean, you can just, I think the way that I was looking at that before is just taking the spectrum just to be from the photons that are generated near the oscillation frequency. So then you could just basically multiply that by the momentum of the photons. So it's basically like a radiation pressure. So it would be basically the pressure that you'd have for one of the solar sails, but divided by 2, because it's just kind of you're spitting them out, so you're just kicking in one direction, you don't get the reflection. So from that point of view, it's much more similar to like a solar sail. Now the actual, like when you do the full calculation, what it'll come down to is there'll be a spectrum. It'll be peaked near the oscillation frequency, but then you will have photons that are at longer wavelengths as well. And that's why we're trying to get into a more detailed calculation, but that's kind of, again, the kind of back of the envelope way of doing it. Yeah.
Right. I was wondering if any of that like the work we did under Quest. I don't know if you remember with myself and Shanwei and Jim with the rotating gyrotropic particles. It got up to really high rotation speeds just based on the thermal difference. I wonder if those rotation speeds would be sufficient to have a dynamic Casimir effect or not, or I don't know. Just kind of was wondering about that.
It's interesting. I don't remember what the rotation speeds were that you guys were suggesting. Do you know what those numbers were?
Gigahertz, wasn't it?
Was it also?
Yeah, it was up to terahertz actually, but of course the thing would fall apart way before then.
Yeah, right.
And I think it took some time. I don't quite remember the exact details, but I know. And then those dumbbells were going. People from Purdue going up at kind of gigahertz speeds, I believe.
Yeah, exactly. And that was kind of our motivation. Well, one of the motivations looking at this kind of dipole approximation is because that actually matches very well with those kind of dumbbell sorts of experiments you're mentioning from Purdue's group. So I think in their experiments, they weren't looking for the generation of any sort of photons, and the photons would be, again, on the order of gigahertz. And so it'd be curious to see if you could have some photons generated, gigahertz photons in those experiments.
Yeah. So I'm wondering with the gyrotropic nanoparticle is already asymmetric, anisotropic, right? It's like,
yeah.
So
yeah, that's right.
Anyway, kind of an interesting thought. Thanks.
Yeah.
Really like your work.
What else we got?
Actually, Jeremy, I had another question, but is it possible to have some kind of nano fabricated structure near your levitated, or it's a levitating particle, right?
It could be. So I guess it depends on what. So we don't have any experiments right now for the dynamical thruster. So you could imagine doing it maybe with just a levitated particle. The experiments we've done previously have been either with AFM type systems or with liquid crystals and birefringent crystals and things like that with an optical microscope. But yeah, presumably if you wanted to do this kind of torque thruster idea, you would levitate it, and presumably an optical trap would probably be the best way to do it. And that would be similar to experiments that people have done previously. And usually those are kind of in free space. You could try to bring it near another surface. That does complicate things. But I think that would also be really interesting, because then you could also do kind of an interplay between kind of a geometric Casimir torque and dynamic Casimir torque. So you could be thinking about how you've got kind of a torque interaction and also generation of photons at the same time. Again, I think it becomes more complicated because the optical fields will change. So your trapping fields will then be influenced by whatever your surface is. But people have definitely done, optical experiments near surface, optical trapping near surfaces, and so it's definitely feasible. But you have to be a little bit careful about the how that affects your trap.
Yeah. Thanks.
Yeah, sure. So actually, since you asked, because I was actually going to send you an email question later, but since we're talking here, I was wondering, since you talked about basically some of the breakdown that you're having with the sails, at what points they would start to, if you accelerate them too fast, then mechanically they start to fall apart. And so maybe I can take this offline later as well, but I was curious to hear your thoughts about kind of best ways to think about nanostructures being accelerated and starting to deteriorate and break apart, because that was one of our concerns, was thinking about how fast can you have an object rotating before it starts to break apart. And so I don't know if you have any comments on that.
It's funny about these rotating ideas, because there's this idea of rotating the sail and getting this to be a way to stabilize the sail. And one of the things that I think I talked to Bill a little bit about this at one point, but that I have some, maybe I think there's some difficulties with that, because your photonic crystal, whether you make a square lattice or a hexagonal lattice or whatever lattice of poles, will always be linearly polarized. So it has to be aligned to a polarization of the laser. So if it's spinning, it's only going to be well aligned once in a while when it's aligned again. And it was kind of back to this thing of not being able to get a feedback. You know, the sales should be a passive structure. You don't want to have to feedback loop some kind of message and try to stabilize it. It should be self-stabilized, but I think spinning it may have its difficulties, but it's also about what can be done on the laser side. If you can circularly polarize things or do something very clever, then I think it's possible. But in terms of like, how do you get this thing to survive? There's also this idea of you can also make things flexible at places where it would maybe break, or if you're carrying a chip, there might be some points at which you hold on to the sail, and that's going to change how you design the structure. Maybe you can make parts that would normally break more flexible or more compliant. Yeah, but it's not an easy optimization problem, because you have these things that are really meter scale, but then have all these nanoscale structure. So you have to find the kind of good way to design that efficiently, because you can't really design the whole thing. Yeah.
Thanks.
Yeah.
I like the back and forth amongst you. That's awesome. I do have a question for Jerry, and I'm glad that Charles is back. It's kind of speaking to some of your hat you wore a long time ago, Charles. I was going to ask Jerry to comment on the difference between the CMFX at University of Maryland, right? This updated fusion test bed compared to, you know, the field reversible configuration, perhaps that folks might be familiar with from Princeton. I think Sam Cohen is the one that pioneered that. Or alternately, I think Lockheed Martin Skunk Works, Tom McGuire had come up with an interesting, fusion concept that had some additional, like that field reversible kind of thing. So, Jerry, I'd love to hear your thoughts, and then Charles, maybe here's some thoughts with you on that.
Yeah, the field reversible types of configurations, and then McGuire's work at the Skunk Works. Both of them are fundamentally different architectures. The FRC is, while maybe it's better to start off with the centrifugal confinement differences. We have, that drift velocity is our operative force, and that does require a fairly high electric field. So that's something that you don't carry with an FRC. The cusp technology is being worked out at Skunk Works. I'm not really sure what kind of amps are running through their system, but again, those are really looking at locally high types of magnetic fields that can be used for a compact fusion reactor. So we're both after the same thing. We just have a different way of getting there.
Thank you, Jerry. Charles, I don't know if you can weigh in or not. I know there might be proprietary things, so apologies.
Yeah, so, well, yeah, a lot about the Lockheed system has been publicly released, and, it's an encapsulated cusp, so it has kind of like a dual magnetic field where it's in a magnetic well, and as the plasma tries to expand out, it encounters a stronger and stronger magnetic field. So in the center of the device is where it's at its lowest energy state, so that's where it's the happiest. Now, we have thought for propulsion that you can change one of the end mirror magnets, and rather than have a recirculation, you would have the energy go out the back end. And so that's a potential application of that. We really don't have any field reverse configuration inside the Skunk Works design.
Mm-hmm.
It's kind of interesting to note that Tri-Alpha down in Irvine, they have a field reverse configuration, about $1 billion investment in that company, and their device just keeps getting bigger and bigger. It is. It's I believe 100 feet now, maybe it's 100 meters. I don't quite remember. And then the neutral beams they use for heating up the plasma. Those suckers are giant too. I don't know. So I'm not sure. I remember Sam's Sam Cohen's field
Right.
reverse configuration somehow seemed cleverer to me, but I'm not versed enough to be able to speak to why I felt that way. But it seemed like Sam had a better field reverse configuration mousetrap than what Tri-Alpha is doing. But that's just my intuition talking.
Yeah, I was just going to mention the Princeton system as well.
Yeah.
Thanks for the narrative there, guys. Any final questions from anybody? Phil, you look like you got one right on the tip of the tongue. Come on.
I was just gonna say thank you, Sonny, and your team for pulling this all together. It's really delightful not only to hear everybody, listen to the talks, which are always great, but just all the work that goes on behind the scenes. It's not like you're just sitting there doing nothing and just waiting for things to happen. You do a lot. So I just want to say thank you and really appreciate what you guys do.
Yeah, thank you, Phil. So a good segue. Appreciate everybody's efforts today and efforts that support all the work that you talked about today. And I know, in a lot of cases, you guys are representing big teams too. So thank you to the extended teams that you represent, right? It's LSI's privilege to get a chance to try and lead in and help a little bit in whatever way that we can. So I'll just open up to the floor. Any final comments before we bring down the loops?
I just wanted to echo Phil's thank you because, as you know, Sonny, how hard it is to get funding for some of this research that is a little more unknown and maybe might not pay off in the end. Always very difficult, almost impossible to get funding for. So thank you for being a champion for this kind of disruptive work that I think is what's really needed to make a difference. And I just wish that, the companies and the government could fund this sort of work more than they do. But so thank you for your efforts.
Here, here.
Good words.
Yeah.
Here, here.
All right. Well, thanks everybody. I appreciate it. Have a good rest of your Thursday afternoon or Thursday morning. Sorry, actually it's Friday for you. That's right. So have a good rest of your day, everybody, and have a good weekend. Thanks, everybody.
Yeah. Thanks, everybody.
Bye, everybody.
Great discussion.
Nice seeing
Thanks,
everyone.
everyone.
Bye-bye.
Bye-bye.
Yes.
Thanks, Sonny. Bye bye.
See ya.
Oh, hi, Sonny.
Yeah. Hey, Remo. Yeah, I was just bringing down the YouTube loop. So
Unfortunately, I had to jump from my university to my home because I closed this during the summertime, so I lost some pieces. But in any case, I would like to thank effectively for your efforts and for this big team. It is very important also for me.
awesome. Thank you, Remo. Really good words. I appreciate it. It's good to see you.
And next week, me and Kirill will be in conference in Italy, in Trieste, close to the ACTP, and we'll present our work, our results, and I will put LSI as a logo.
Awesome. Sounds good. Get somebody to take a picture with their iPhone while you're up there. Send it to us, and we'll post it to social media.
Okay.
All right. Okay. Sound good?
Okay.
All right.
Bye-bye.
Thanks, then. See you, bud.
Bye.
Bye-bye.